Hello? 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 Hello?
All right, welcome anyone who has decided to join me for the Gamestack stream. I just need to ask a quick question because there are two upcoming events at the same time, and I don't want to like mess with my stream setup. But so I need to know which one people are more interested in watching. We have graphics keynote delivering the next generation of gaming graphics, or Xbox Velocity architecture, faster game asset streaming, and minimal load times for games of any size. So just sound off in the chat on whatever you wanna um, see me broadcast, and I'll pick that window. Whatever you think is more interesting. The one I'm planning to watch is Velocity architecture. I mean, well, I like them both. So, and plus, I have two windows open, so I'm going to get to watch both. But yeah. I just want to know velocity. So it sounds like people are more interested in velocity architecture. All right. Unless anyone has any objections, we'll go with velocity architecture then. Hold on, I'll be right back. All right. Yeah, velocity is good. Okay. I hope that my mic isn't too sensitive and you can't hear like my PC fans or whatever going in the background. Um, I have no idea because I had to mute my own stream, otherwise I was getting severe echo. Why is... Oh, hold on. 1 second, phone call. Apologies. Why is the sound low? I don't think... Is the sound better now? My mic is like kind of crappy, and there's graphic. We're going to do the velocity architecture, unless anyone has any unless people all of a sudden want to do the graphics one. I mean, like I said, I will be able to watch both on my screen, but I don't want to have to set up like a Gamecaster to be able to broadcast both. And also, I don't think that 1080p is enough to really get a good picture out of trying to broadcast two at the same time anyways, so we're just gonna stick with one. Yep, sounds better. Okay, sounds good. Yeah, my mic is not the greatest. It's an older SteelSeries headset, so a couple millimeters here or there can be the difference between too loud or too quiet. We got about 2.5 minutes. What's poppin'? Not much. We're just waiting to get started on our first stream. The other one I'm planning to watch is Spatial Audio and Project Acoustics. Oh yeah, that's really cool because that's like there's no way you could even no amount of money could buy you like a PC that could simulate the Project Acoustics slash what's it called, Triniton audio in real time. It has to utilize what's it called? It has to utilize the Azure cloud to bake it, and then you can use the Project Acoustics or your. See, my body's Reggie. Oh, I'm Gabriel. Hi. Oh, hi. Good to see you. Yeah. All right. I'm gonna see if I can load up our talk here. good to go. Let's see, what is it?
Hi, welcome to Gamestack Live.
All right, here we go.
My name is Mike Sterling, and I'm a program manager on the Gaming Experiences and Platform team here at Microsoft. Today's Gamestack Live session is Xbox Velocity Architecture, faster game asset streaming, and minimal load times for games of any size. During today's session, we will first start with an introduction to the concepts that make up the Xbox Velocity Architecture. We'll view a demo, and then lastly, a call to action. Existing technology has significant bottlenecks when looking at running games on the Xbox One family of consoles.
Thanks for streaming it, no problem.
First of all, the read speeds of hard drives don't scale. Hard drives cap out at about 120 megabytes per second of read speeds in optimal conditions for gameplay. With the move to more flash-based memory solutions, those read speeds are increased by an order of magnitude. That is why we have seen the industry move towards more flash-based solutions such as SSDs. Additionally, there's a significant CPU dependency. Issuing the read calls, waiting for data, decompressing, and closing the handles, all through the Win32 instruction set,
I don't know
reduce the amount of
hard
CPU cycles available
for
to a
anything
game.
outside of
This is because of the built-in inefficiencies of the Win32 command set when working with much larger modern titles.
Yeah, my bad.
And these issues impact all areas of gameplay. When you look at how traditional games are developed, games are broken up into a series of assets. Those assets can be something as simple as a texture that is placed on a box, or it could be something more
idea what Miles and Jez
like an AI
about?
for somebody that you're going to be following
what
around
the context
in the game.
around that.
Those chunks are then
maybe I'll look
loaded
into it later someday.
I
mean, I've got a full plate with all this Gamestack stuff.
As I mentioned earlier, the traditional load speed of
wow,
hard
that's
drives
nice.
has
I wish I could have a 2 terabyte
severely
SSD.
The amount of time that users are actually able to play because you actually spend more time loading those assets. I've lost track of the number of times where I've started a game and I've had to wait a minute to get to the loading screen, and then another minute after I actually start the game before I can actually interact with it. We want to be able to get users into the game quicker.
It's still not full screen yet, FYI. Hold on.
So that's
you mean this thing? Hold on,
of the Xbox Velocity Architecture.
Shoot, give me a minute.
As games continue to increase in complexity with these rich, immersive graphical and audio experiences, there were really 3 things that we wanted to address. First of all, as I mentioned earlier, we wanted to minimize the amount of time being spent on loading screens. Secondly, we wanted to enable a longer or larger draw distance. Imagine being able to see across the map while you're playing Halo.
Kirby's gone. It's not a big deal.
As we have seen, more games are becoming open world. Open world games provide a unique set of challenges, and the main issue that we wanted to address with the Xbox Velocity Architecture was being able to quickly travel between 2 different regions without having textures pop in. We want to maintain that immersiveness. So, the Xbox Velocity Architecture consists of 4 components: the SSD, direct storage, hardware decompression, and sampler feedback streaming. The SSD that's included within the Xbox series of consoles, both the Xbox Series S as well as the Xbox Series X, is a high-performance PCIe Gen 4 NVMe SSD. We worked very closely with our suppliers to develop custom firmware that is designed specifically for Microsoft and the Xbox. This firmware allows us to guarantee 2 gigabytes per second of read bandwidth
Kiss any chances of homebrew SSD or SSD upgrades goodbye.
But that data is generally compressed. Another feature of the Xbox Velocity Architecture is native hardware decompression.
Nice. I will have to check that out. Maybe some thermal throttling.
In previous generations of consoles,
it's supposedly designed, both the internal NVMe and little memory cards are designed to combat that and not have to deal with thermal throttling.
This saves CPU cycles,
which is why
allows for closer integration with additional features in the OS.
Much heftier or denser than it looks because there's
using
big
direct storage, it can decompress content directly into memory. The hardware decompression block includes support for both BCPAC, which is a Microsoft standard for texture compression, as well as zlib using the RFC 1950 standard. I mentioned direct storage. Direct storage is a new feature that we developed specifically for the Xbox series of consoles.
Yeah,
and it works hand in hand with hardware decompression
the direct storage stream
to provide
so supposedly someone just said that they are talking about direct storage coming to PC
in bypasses the entire Win32 IO stack
graphics stream
and allows for direct access to the underlying
I'm not actually
device.
watching it because I have to go full screen
because of the amount of overhead that comes with the Win32 IO stack, as I mentioned earlier,
on the PS5,
especially when paired with sampler feedback streaming.
That's Sony's problem.
The drive needs to be able to read data as quickly as possible to remove any sort of texture pop-in or bottlenecking.
Yeah, I think that's in 2 hours.
I mentioned sampler feedback streaming on the last slide.
I'm only now able to watch one because I'm going full screen so you guys can actually see it.
It's also known as partial residency of textures in Direct 3D. It's also known as tiled resources or reserved resources. However, up until now, it's seen very limited adoption in the marketplace
limited adoption
of the speed of storage not being able to keep up. So, with sampler feedback streaming, we designed the feature to instrument shaders to identify what is visible within a player's field of view and only load in the textures that are necessary for that field of view.
No problem.
That gives us a leap in efficiency, and it allows us to dedicate more resources that would otherwise be used for the rendering of those resources. You could then use those additional CPU, disk, and graphics resources to provide more experiences to your users. Let's take a look at how you can use game asset streaming.
The scene you're looking at was built to a very high level of detail.
This thing from the Series S tech demo.
Over 10 gigabytes of texture content are present in the scene.
Wow.
And we use texture
they have 10 gigabytes is the entire physical memory of the Series S.
A traditional texture streaming engine decides to load texture MIP levels using a coarse measurement of which objects are visible and how large they appear on screen.
Yeah, we know. I know that this was on the Series S, but I didn't know there was 10 gigabytes of data in this scene.
This memory size is known as the texture budget.
Them saying anything
about
that.
And in most titles, the texture budget is the largest single user of title memory and the largest single user of storage.
Whoops, I paused it.
We can estimate what an optimized Generation 9 traditional texture streaming engine would need to have in memory to render what you're seeing
they can
right
cut
now.
Down on about
it's still a conservative estimate, by the way.
That's
most game engines would likely use somewhat more memory than you see here due to overstreaming.
Damn, this can be
but with sampler feedback streaming, we can use significantly less memory to render the same scene,
megabytes versus
and a corresponding reduction in the amount of storage we use to load the data into memory. That means that for the same scene, we're loading it faster on Xbox and using less memory than on competing
FPS.
platforms.
Well, it's a simple static scene.
We think of this efficiency gain as a multiplier on our storage performance and our graphics memory size. With this view of the scene,
hey, don't be afraid to use naughty words in my stream because I don't monetize my YouTube channel, and so I don't really care what the Google Plot Police thinks about what I have up here.
They aren't all that high, especially compared to the 10 or 16 gigabytes of memory in our consoles. Our content in this tech demo is fairly simple. A real AAA title would likely have significantly more complex materials and more objects visible. Crucially, however, the comparison between sampler feedback streaming and traditional MIP streaming holds true regardless of material complexity. The numbers will scale with content, and the multiplier will still ring true. Let's compare a Generation 8 traditional streaming engine on a hard drive to sampler feedback streaming running with the Xbox Velocity architecture. I'll start the scene reload now. This camera angle consists of over 2 gigabytes of texture data and simulating a hard drive from the Xbox One X console. It'll take a while to reload all of the data needed to render this scene with its ideal level of texture detail. From talking with title developers, we know that texture streaming is as much art as it is science. Various techniques are used to estimate scene visibility and size for each object, and then calculate how much texture detail must be loaded for each object to make the scene look great. Most titles do complex offline processing to make these estimates better.
Because,
some titles show a load screen while textures are streaming. And even after all of this engineering work is done, artists usually need to manually adjust some objects and textures to fine-tune the results. It works, but it's a lot of work. After about 22 seconds on a simulated Xbox One X console, we're done loading. Now, we reload the same scene using sampler feedback streaming from our solid-state drive. It takes less than a quarter of a second.
Yeah.
If you missed it, let me replay it for you.
0.91 seconds. That's very
Sampler feedback uses the GPU to automatically determine the exact set of texture data needed to render the scene with the ideal level of detail. Our solid-state drive, hardware decompression block,
frames at 60
and
frames per
optimized
second?
direct storage API gets that texture data into
I'm
memory
working on it right now
quickly.
in Void 2D and Void 3.
The Xbox Velocity
it's not
architecture
easy
gets you into the game
to implement,
quicker.
but
The game spends less
when I
time
look at this,
loading
I'm
data
like,
that it doesn't need for that
it's
first
totally going to be
frame
worth the
of
work in the
action.
end because of the gains we're getting.
Additionally, you can see that I can fly around this scene and the system easily keeps up. Thanks to the efficiency of the Xbox Velocity architecture, you rarely see pop-in artifacts. When you're playing a game, sampler feedback streaming allows you to move quicker through the world with higher detail.
And since
everything loads so quickly, game developers don't have to use twisted hallways between areas or loading screens to cover up texture streaming. There is a ton of detail in this scene.
That is something
when you get close to the drawings, you can see the texture of the paper as well as even the pencil strokes. And you can see how the memory usage changes as I look at different parts of the scene. You'll note that the memory bars in the upper right-hand corner consist of both a light region and a dark region.
Yeah, I was wondering what this was.
The light region represents the amount of memory seen in the previous frame, while the darker region represents the amount of memory that is loaded but was not used in the previous frame.
Oh my God,
the streaming system is constantly unloading memory that hasn't been needed for a few seconds. So you can see here that as I move, and if I stop,
talk in between the audios. I'm sorry.
The darker region soon shrinks to almost
take
zero.
A gap when talking. I do have captions on. Are they visible? I hope they are.
I can even do quick camera cuts, which are difficult for most texture streaming systems to handle. Each time I perform a quick camera cut, over a gigabyte of new texture data can come into view. Thanks to sampler feedback streaming, only a fraction of that data needs to be loaded. Some games have to have a lengthy load screen, transition effect, or some sort of contrived gameplay element to hide the texture.
As far as we know, there is no the PS5 doesn't have sampler feedback streaming.
This tech demo doesn't have any of those tricks.
Obviously, Sony could totally come out and like confirm it, but they haven't, as far as I'm aware.
Earlier, I talked about loading texture pieces.
And I just want to say,
I talked about loading textures piece by piece.
If you don't, I'll do what I want. If my audio is messing up, we don't have the greatest upload internet speeds in the world, so that might be part of the reason. But
from red representing the most detail to purple representing the least amount of detail.
I believe they will post all of this on demand on their Gamestack YouTube channel,
which memory is loaded for the texture we're focusing on.
When do you think
each texture in the game is implemented with multiple levels of detail?
Again, like I've said, probably alongside all of the other DirectX 12 Ultimates and Xbox Velocity architecture,
has the most amount of detail,
adoption timeline.
So has half the dimensions of the previous.
Maybe late 2021 at the very earliest. More likely 2022 and
MIP levels
beyond.
are used to increase performance as well as improve image quality when objects are drawn far away from the camera. First, I'll show what traditional texture streaming does as I approach the drawing. Entire MIP levels are loaded into memory regardless of what piece of the image I'm looking at. And as I back away, the texture streaming system can choose to unload the more detailed MIP levels when they're no longer needed.
Oh, that's funny. Needed. The blocks say Xbox XVA
Note
on
that
them.
These MIP 0 images are rather large.
I think there's also a little thing in this tech demo where one of there's like a box that says PIX, fun for all developers.
Even with a solid state drive,
which if you don't know, PIX stands for Performance Imager for Xbox,
just to see detail for
which is
one
the
texture
tool
on one object.
Debug,
considering the number of texture
DirectX
layers
apps.
on each object
Keep
and
talking.
the number
We came
of
to hear
objects
reaction
you can
after
see
the
at
okay,
once,
yeah, I'll keep
these
it up.
high detail MIP levels can really add up. With sampler feedback streaming, however, the system can load these MIP levels bit by bit. It's more responsive because it very quickly loads the detail only where it's needed. It's more efficient because it doesn't load the detail where part of the drawing is off camera. Think about standing next to a building or a statue in a game. You want to look at part of it up close. Sampler feedback streaming allows you to see incredible detail up close, like the placard on a statue, or the face on this drawing. And it doesn't waste time or memory loading unnecessary detail far away from the camera.
God, I wish I had this feature on the Switch, and I cannot wait for the Switch Pro.
Games can add more detail to every object,
to reach feature
large
level
and small,
12.2 or
and
Switch
not have
2
to
or
worry
whatever.
about compromising their entire texture budget elsewhere to make it work. Next, we'll look at this globe hanging from the ceiling. Sampler feedback streaming uses data from the GPU to stream in only the visible parts of objects. In this camera
this would be
angle,
awesome on the Switch.
the Pacific
the
Ocean
memory
on the
is
other
a bit
side
of
the globe
it's
is
not like impossible to work with, but it is,
However, as I spin around the
nuisance.
object, the streaming system quickly loads in the newly visible parts.
Does that say 1,294 FPS?
No
yeah,
visible.
the FPS is insane because it's
Think
just like a
in-game
super simple
cinematic
tech
when
demo.
You see a character's face up close. Sampler feedback streaming
it's not
allows that
representative
character
of
to have
real-world
incredible
performance,
detail
obviously.
loaded extremely quickly.
Earlier,
not waste
what they
time
said,
loading
though, is
detail
that
on the
obviously
other side of the
a
character
real
he
AAA
can't
game would be
see.
much more complex than this. But what's important is
Now
that
I'd like to
the
show you how our
principles
sampler
of
feedback
sampler
hardware
feedback,
feature works.
memory,
I've
or effective
re-enabled
memory
scene color
multiplication
coding, and I focused
still
in
apply
on
no
this
matter how
drawing
complex
on
the
the
scene
easel.
is.
On the left is a visualization of sampler feedback data for this one texture. Sampler feedback is configured
Sadly,
per
Vulkan doesn't have
texture,
something like SFS
and we
right
are
now.
looking
Yeah, I
at
know,
just
that's a
one
bummer.
of the 475 textures in this scene that
Okay, damn,
are
I
all
was about to say
producing
that's
feedback.
some crazy numbers. Yeah,
The
that
texture
happens like
is
with,
divided into
like,
regions.
when you
and the
initialize
developer chooses the
Direct3D,
size
like
of the regions.
just with a blank window, you'll get
For
like
each region,
12,000
the GPU
FPS,
computes
which
the
obviously
ideal
is
level of
not
detail
real.
used to sample the texture.
This is a game changer. I
within
hate
that
zooming into an
region.
object to see the bad textures. Yeah,
As I approach
hate that too.
and pull back from the drawing,
you'll
you'll
see
see
these are
regions
not the
of
days of the
feedback show
N64.
higher
We
and
can have
higher
better than
levels
that.
of detail, and then you'll see gray. Gray represents no feedback. That's because those regions are now off screen. You may also see some random flickering in the sampler feedback data. This is because we're capturing only a fraction of the sampler feedback data. The GPU is capable of providing an enormous volume of sampler feedback data, and we can carefully tune the level of output to best balance accuracy and performance.
I mean, it's going to depend.
We have found that we can discard over 99%
it's going to depend
of
on
the raw data and
game
still
versus
get
game.
great
I mean,
results.
you look at games like Minecraft DXR, where the ray tracing is like, normally the game can run extremely well,
can tune sampler feedback
but you turn on ray tracing and
if their needs.
You pretty much need DLSS and a good ray tracing GPU, or it's just going to hammer you hard.
Now that you've seen the benefits of the Xbox Velocity architecture,
then you have other
you can
games
see
like
we're so
Metro that
excited
supposedly
about
are doing
we encourage
60
all
FPS with ray
developers
tracing
to
on the
adopt
console.
the usage
So
of the Xbox Velocity architecture
I guess
for
it's just
rich,
going to depend.
immersive experiences on both the Xbox
if you're
Series
using
X
DLSS,
and the
DirectML, or
Xbox
Fidelity
Series
FX
S
Super Res.
consoles.
They explain it really well.
The usage of direct storage and the hardware decompression functionality allows you to quickly read the data and make it available, while using sampler feedback for streaming to only load the assets that are needed for what's in the player's field of view. For more information on game asset streaming, at Gamestack Live, we have 2 sessions. We have a Getting Started with Direct Storage session, which focuses on direct storage for Xbox. Additionally, we have a session on direct storage for PC, which uses similar concepts, but the feature is still in development. If you are an Xbox developer, there are more details available on the Xbox Velocity architecture and the Xbox documentation, and you could also follow up with your developer account manager for more information. Thank you for attending today's session on the Xbox Velocity architecture and game asset streaming.
They didn't say when the Xbox hardware compression block is actually going to start being used. That's a bummer. All right, I'm just going to exit this. All right. Fidelity effects now available for Xbox. What are you just? What kind of fidelity effects? Like, it's been available and it's been used in games like Gears 5 already. Are you talking about fidelity effects super res? Did they just release that or something? Hold on, let me pull up GPU open. I don't see it on GPU open. Is there any BC Pack examples? Not yet. Like I said, the hardware compression block is not currently in use on any of the Xbox games. I don't know why. I think this is the whole GDK maturity tools kind of thing being behind because of the wait for full RDNA 2, etc. So yeah, no. I mean, you can go look on Microsoft's DirectX documentation on what BC Pack is, but as in terms of real world examples, on the 9th gen consoles or 9th gen Xboxes using BC Pack, there are currently none. Not super res, I don't think. Probably not. Yeah, no. Don't really. Yeah, if people get fidelity effects and fidelity effects super resolution confused, it's at the end of the graphics keynote. All right. I mean, I'm gonna have to go back and watch it later, because shoot, I gotta hold on. I gotta see what's next on the schedule. Give me a minute. It is noon Eastern. So, next up is just a single session, Accelerating DirectX Innovation, and that starts in about 20 minutes. So, I mean, I'm going to keep the stream open. You can stay here if you want. I'll be streaming all the way until about 4 p.m. Eastern today, which is the end of the ray tracing with Minecraft, which is presented by NVIDIA. Nice. Yeah. Their DLS solution, whose? AMD's or Microsoft's? Or both? Base Kirby. Yeah, thanks. Microsoft? Yeah, I really do hope that they that DirectML super resolution is good. I mean, just looking at what was it? The demo they did in 2018 with NVIDIA looks already very promising, and I believe Jason Ronald said on a podcast, I think it was the Iron Lords podcast, I'm not entirely sure, but he said that that Microsoft is, definitely planning on supporting machine learning super resolution, and yeah, we'll see. The thing is, NVIDIA has dedicated hardware. You have the tensor cores, the DLSS likely rate. Yeah, I think DLSS just honestly, for me, it's more about, I guess, I mean, this is a personal thing, but what I like from DLSS is, or super resolution techniques in general, is whichever one has is like the highest quality highest image quality. Like, I would rather not sacrifice a ton of image quality to boost performance. I mean, obviously DLSS and DirectML Super Res and FSR are going to boost performance, just because that's their super resolution features. But for me, it's personally like, I like whatever is going to give me the highest image quality while also a decent FPS boost. Maybe that's not the same for everyone, but that's just how I feel about it. I mean, yeah, image quality is very important. I agree. Yep. Same. Yeah. I'm gonna ask a question. So, as far as I can tell, using same back in 20. Okay, thing is, DLSS sometimes gets badly implemented. Yeah, I know. Almost everything about DLSS 1, I was not a fan of, but 2 is much more. In Cyberpunk, for example, TAA is sharpened by an aggressive amount, while DLSS sharpening is completely inactive, which leads to people think it's blurry. Yeah, that's unfortunate. I don't like TAA personally. I will opt to use an alternative anti-aliasing method in PC games if that's an option, even if it's like not the ultra preset. Like TAA is considered a higher graphics setting. I just feel that TAA is a bit of a blur filter. So, hey, dude, I didn't know you had a YouTube. Yeah, well, I don't post much stuff on it. I've been trying to do it. Once HDMI 2.1 capture cards come out, then I can really start hitting the YouTube streaming, because there's no native streaming from the Xbox Series X to YouTube right now, and you can't use Restream now that Mixer is shut down. So currently I'd have to give up HDMI 2.1 features in order to stream to YouTube directly. So, yeah. What I am doing is streaming to Twitch, saving the VOD, and then going to re-upload it sometime later. Fidelity effects is available today on X. Yeah, certain fidelity effects, many of the effects are available right now. Not the super resolution yet. Yeah. Yeah, TA is blurry sometimes as well, which is why many devs implement sharpening. Looking forward to your Twitter post in regard to this. Thanks. Do you think games like Forza Horizon 5 will come this year, use mesh shaders or sampler feedback? I don't think so. I mean, I guess it's possible, but like I said, I personally think that the realistic timeline for like full DX12 Ultimate and Velocity architecture is 2022 and beyond. These are simply not easy features to implement in a custom engine, and for people who are using like canned engines such as Unreal. Like Unreal Engine 5 is not, which is going to support all this stuff, isn't public release until I think fall of 21, and then obviously it takes time to make games with those. So I don't think we'll be seeing really full DX12U in any form until 2022. I think Fidelity Fix has some good techniques. Yes, it does. I like that it's open source and it can be optimized on both GeForce Radeon and I guess Intel. Yeah. CAS is the best sharpening filter. IMO. The new FX SSRs look cool too. Yes, they do. I agree. Hey, why isn't the video playing on? Because the session is over. In 10 minutes, the Accelerating DirectX Innovation stream is going to start, and I'll play that. Twitter notification. All right. Boy. Have you tried out MetaHumans? It's incredible. No, I have not tried it out. I'm just so busy, like between taking college courses and working on my engines and just doing stuff in my free time that I enjoy. I have a pretty full plate. That's it. But though I should try out MetaHumans sometime. Oh, man. Playing Fallout 4, listening to this awesome conference with great takes from you in the chat. Oh, thanks. Oh, yes, I can imagine. Yeah. Life's rough. I've already created some characters and have imported them to UE4. It's really amazing what's possible. Well, that's awesome to hear. I didn't know that you were doing some development of your own. That's cool. Maybe life really is the Matrix, lol. Maybe. Who knows? Your question was answered, by the way. Ah, thank you. Okay. The decompression block is currently supported as part of the Direct Storage API. The decompression options are specified as part of a destorage underscore. Well, come on. Request structure. Great question. Yes, DK is still in nascent stage, so you are still yet to see true next-gen titles leveraging SVA. Interesting. I always wondered about this. Okay, well, perhaps ID at Xbox hasn't gotten that documentation yet. We get to be last in line. I'm just toying with it on, not trying to be a game developer. How hard is it to implement VS Tier 2 mid or late development? Well, I can say that for a fact that the Coalition implemented Tier 2 variable rate shading into Gears Tactics and Gears 5, which were already existing games on an already existing engine. So and plus when you consider that AMD's got their Fidelity Fix variable shading technique that's open source, I don't think it should be too hard to implement Tier 2 VRS on top of existing engines or games. I mean, also look at, if you remember the AMD RX 6000 presentation, like they showed a lot of games that they were really pushing their variable rate shading tech pretty hard. So I think obviously it is something that developers are finding easy to implement. Nascent state, yeah, nascent just means like early. Let me actually define nascent. Nascent, especially of a processor organization, just coming into existence and beginning to display signs of future potential. So yeah, it just means it's young and yet to be matured. Gears 5 variable rate shading is pretty efficient. In some cages, I get like 10 more FPS in dark spots, of course. That's nice. Assuming what resolution is that at? 1440p, 4K? I know the coalition said that variable rate shading helps them get. They're still using dynamic 4K, but they said it gets really close to native mode or at native most of the time with VRS. 1440p. I'm assuming you meant. That's not bad. Yeah. Yeah, I would imagine variable rate shading is going to help a lot more at higher resolutions because it's more opportunities to not have to run the pixel shader as many times. Personally, I can't tell a difference. Lol. Yeah, well, that's the idea, which is great. I'll take 10 FPS for unnoticeable image quality improvement any day of the week. Oh, coof coof. Kirby, I thought you were a girl. When did I? Come on, you can't judge a person by their avatar. As far as I'm aware, I never claimed to be a girl. But Louise is best girl. Lol. Yeah. Do. All right. Less than 2.5 minutes to go. Going to pull up. Accelerating DirectX innovation. It won't let me in yet. Let's see. MSI just put out, congratulations, MSI, for reaching an incredible milestone of 3 million gaming monitors sold. MSI has remained an outstanding partner for GeForce, and we're looking forward to more accomplishments in the future. NVIDIA GeForce OEM General Manager. That's nice. What are your thoughts on Omniverse? I think the NVIDIA thing, yeah, I think that's like super cool. I can't wait to see what comes of that. You know. All right, I'm gonna go see if I can pull up. All right. We'll say that was good. All right. Hold on. I'm gonna reload this. So SFS is a game changer for Series S, definitely. Yes, I mean, it's a game changer for every device every graphics card that supports it. From the lowly GTX 1650 to, the mighty RTX 3090. What is going on here? Why is my stream not going? They are some very impressive Marvel RTX assets. I've loaded them to Onverse Create. They're so lifelike. Well, that's great to hear. Series S will be the wild card. Yeah, definitely. What is going on here? Why is my... Okay, whatever. Why is my 1220? It should be available. We want to allow autoplay. Come on. Finally. Benefit from so much. Yep, same as Series S. Yep, I definitely agree.
Hi, my name's Jacques van der Rijn, and I'm a program manager in the graphics team. Today, I'm excited to share an exciting update to DirectX. It's an update that's going to accelerate graphics innovation, vastly improve the developer experience for bleeding-edge game devs, and ultimately help gamers get the most out of their new hardware. Let's dive right in. I want to start this presentation by quickly talking about how feature updates for DirectX 12 works today. Since the start of Windows 10, we've relied on the Windows 10 OS to get the latest DirectX 12 features onto Microsoft's huge install base. Put another way, every update to DirectX makes its way to the next OS we ship out to Microsoft's 1 billion plus Windows 10 devices, as you can see in this graph here. Here we see how we ship variable rate shading in Windows 10 version 1903, or the May 2019 update. And then we ship the full DirectX 12 Ultimate feature set in Windows 10 version 2004, or the May 2020 update.
He's got a cool t-shirt too.
With the OS as our next ship vehicle, the next chance we'd have to get support for a new feature like Shader Model 6.6 out is with the next major update of Windows. Doing this means we have a guarantee.
DirectX 12 Ultimate, yep.
It's a guarantee that the new features we implement gradually make their way to reach a massive audience of Windows 10 users. It's something that means that eventually gamers and developers all get access to the groundbreaking technology that we've been using to push graphics innovation for generations of hardware and consoles. It's a model that works, and we're proud of all the work that developers have done using this guarantee to build games that run on this huge install base.
Wish there's a way to light them up faster on their entire
top of the list of feedback we've heard from our developer partners is that they're excited about our features,
especially
so much
right now.
That they wish there was a way to get our features sooner and up and running on a massive install base, not just the latest Windows 10 OS. Well, we're excited to announce that we're giving developers just that with the DirectX 12 Agility SDK. With the Agility SDK, all DirectX 12 features, new and old, run on a massive install base. Every OS since version 1909 or the November 2019 update has support for all the features we're lighting up with the Agility SDK. The Agility SDK is also a way for developers to build games that use our newest features when they're ready, even before those features have begun rolling out with the next OS. Best of all, games that use the Agility SDK will run on a wide range of gamer machines today without ever asking gamers to wait or to upgrade to the latest version of Windows. Today, this means that the latest from DirectX, including DirectX 12 Ultimate and Shader Model 6.6, will run on every Windows 10 OS version 1909 and more recent.
I'm not really bothered by them, but some people are.
Now, we have exciting details to share from the studios we partnered with, but first, let's talk about what the Agility SDK means for you, whether you're a developer or a gamer. Our game developer partners have told us they needed our latest innovation, including DirectX 12 Ultimate on older OS versions, not just the more recent versions of Windows 10. We did just that. the Agility SDK lets developers bring our latest features to a large install base on day one. We brought OS support all the way back to the November 2019 update to ensure that developers can be confident that their games using the Agility SDK will light up features for a huge audience of Windows 10 users. We also built the Agility SDK model from the ground up to be easy to integrate into existing game engines. Later on in this presentation, I'm going to go over just how straightforward this is. With the Agility SDK model, the DirectX team has a way to get fixes and tweaks out way faster than ever before. When we fix something, we'll simply issue a new SDK with the fix, instead of asking devs to use workarounds while they're waiting for a fix to make its way to the OS, through Windows updates or through the next major version of Windows.
It seems like they've decoupled
the same goes for tweaks and adjustments to our features. Now it's easier than ever to get our latest changes into the hands of developers. For bleeding edge features, developers no longer have to grab the newest Windows Insider program.
Oh, good, because I'm not part of Windows
Insider. Just grab the newest Agility SDK.
I'll be able to finally get the FL12.
The choice to use the Agility SDK is purely optional. Devs who don't need or who don't want the latest hardware features can carry on like normal. We are still going to keep on adding and shipping the latest updates to DirectX 12 to the latest Windows 10 OS. Now, each Agility SDK contains all the parts you need to get started with developing and shipping games with the latest DirectX 12 functionality. Check out our landing page to get started developing right after this talk. Go to aka.ms/DirectX12Agility. Here you'll find links to our first SDK, our announcement blog, and a link to our Getting Started guide. Our first Agility SDK contains support for the full DirectX 12 Ultimate feature set.
Nice!
And like I mentioned earlier, every OS with the November 2019 update can run Agility SDKs. This means that the full DirectX 12 Ultimate feature set can now run on an even larger install base than ever before. That's right. These features that used to be limited to devices with the May 2020 update and more recent can now run on more gamer machines today. Our first Agility SDK also has something that's so new that support for it hasn't even made its way into the OS. I'm talking about support for shader model 6.6, which Greg Roth is going to cover in his talk. Whether you're interested in expanding the reach of your existing DirectX 12 Ultimate capable game, or you want to catch a glimpse of a brand new update to DirectX, the Agility SDK is for you. Now, we know we have gamers in the audience too. What does all of this mean for the rest of us? Well, put simply, what's good for developers is what's good for gamers.
What's good for devs is what's good for gamers.
We're talking more games with bleeding edge features. The Agility SDK removes a barrier for developers who want to use our latest features, but who also want to wait to make sure that their gamers can actually access these new features. These developers will often wait until an OS with our latest features reaches a large enough audience of gamers, which can take some time. With the Agility SDK, there's no longer such a waiting period. Put another way, your new hardware's capabilities become real faster. When you buy brand new hardware, you can feel good about upcoming games making the most of the cutting-edge features on your new device.
Yeah, it's a good sign. Yep.
I'd like to chat about the work we've been doing with our partners in the games industry leading up to today's announcement. We've been working with Epic Games and other studios on the Agility SDK, and we've been incorporating their feedback to make sure that our first Agility SDK is ready for you to bring to your game today. This is just a sample of the feedback we've gotten so far, and I want to make sure that we have time for Q&A at the end of this presentation, so check out our announcement blog to see what our partners have to say about the Agility SDK. A bit later in this presentation, I'm going to show you how you can get started as well, and how to give us the same kind of feedback that has shaped this project from the start. Before I dive into how to use the Agility SDK, I want to talk about how the Agility SDK model works from an OS perspective.
Okay, thank you for letting me know. Hold on.
The DirectX 12 runtime, D312.dol, lives in System 32. The simplest explanation is that games that use DirectX 12 use the functions in this DLL. Now, we had a constraint when we designed the Agility SDK model. With any change we wanted to make to the OS, we needed to make sure that games that use D312.dol carry on working as normal,
much better,
while still giving developers who want newer functionality the option to do just that.
That's fine.
So we took this DLL and we split it into two. Now D312.dll is just a thin loader that most of the time will just load in D312core.dll, which now
that's going to be good because now that's going to cut down on the amount of people who try to those sites that like offer DirectX DLL downloads that just pack malware into them. Like if you see this huge download file, then you're going to know something's up.
It's almost as if the change I just mentioned earlier never happened. And this is by design.
No problem.
Because we needed to make sure that the default experience for gamers and developers remains the same as before our change. Now, I said this is how it works most of the time, because our loader can now also load a new D312 core, one that the developer using the Agility SDK will include with their game to light up the latest D312 functionality. In this case, if I'm a developer who's built a game with the Agility SDK, I'll include a copy of the D312 core that was in the Agility SDK that I used. I'm going to talk about this a bit more later in this presentation. When a newer D312 core.dll gets included with a game install, meaning one that's newer than what's in the OS, our loader will load this newer D312 core. And that's pretty much all there is to it from an OS perspective. I'm about to get into how to get started, but before I do, one key point. Some of you might be wondering, wait a second, if I'm a dev who's built a game using the Agility SDK today, what happens when the next OS ships? Well, we in graphics are going to keep on shipping updates to DirectX, which means that newer OSs will have newer D312 cores. When an OS has a more recent D312 core than what a game shipped with, the OS version of D312
this is going to be good because like not every game would always ship
this way,
with
we can make sure that the latest, highest quality, and most validated DirectX 12 functionality
for whatever reason,
eventually gets used
copyright,
by all
file
games.
size, I don't know, but
it also means the game developers
like I
don't have
meant,
to
the
worry
aforementioned
about
having to go to
using the
sketchy
latest version
websites on
of
the internet to
DirectX,
download
or about a game's version
DirectX
of
DLLs may very well be over.
This will
now
happen
if
automatically
every game
once
is
later versions of DirectX 12 roll out with later versions of the OS. Before I get into how to get your game to work with the Agility SDK, here's what you need to do to set up your dev machine. We're going to go over this one by one.
Visual Studio,
like with many DirectX features, you want to make sure that you have the right OS,
I have the latest
and
GeForce drivers. I'm sure I have them. Latest shader compiler. Oh, I missed it.
Double checking you're on the right OS is simple.
I'm sure I have.
Just go into About in the Settings menu to check your OS version. As long as you have 1909 or above, you're good. One thing to note here is that the OS change that I just talked about has been made to 1909 and more recent via a Windows update, which has had a fair bit of time to roll out onto these OSs. The number that appended to your OS build number, the revision number, gets incremented with each update or KB patch that your OS gets.
In case you're wondering, there's an easier way to do this, is to just press Windows and R to pull up your run dialog, and then just type WINVER
like you can
and
see
enter.
above, or equal to or greater than 789 for versions 2004 and 20H2, your OS has received this patch with support for the Agility SDK. No worries if you didn't catch this info the first time. You can find this information and more on aka.ms/DirectX12Agility. Next up, we recommend that you use Visual Studio 2019. The free community version works if you don't already have the professional or enterprise editions. You then also need drivers with support for the Agility SDK. The Windows 10 SDK comes with a copy of the DirectX shader compiler, but if you're using shader model 6.6, you'll also want to go to aka.ms/HOSL to get the latest shader compiler.
Obviously, I'll have to download that, but that's easy.
Finally, we also recommend that you go and grab
PIX. Yeah, that was the last thing.
As native Agility SDK
I've got that handled. So yay, looks like I am fully ready to use Agility DX12 if I want to.
We'll have all of these links and more on our Getting Started guide. Go to aka.ms/DirectX12Agility. Okay, so your machine is set up. You're on the right OS version. You've got Visual Studio, drivers, the shader compiler you want to use, and PIX. What's next?
It's really straightforward.
This means you're very agile. Haha, good one.
And I've got a little demo that shows how to do this inside of Visual Studio 2019. In your Solution Explorer, right-click on your project.
Ooh, he's working with mesh shaders.
And go to Manage Needed Packages. Here I'm using a local folder as the package source, But you can also grab our Agility SDKs online from Nuga.org. I'm also using a preview SDK in this demo. Anyway, select the Agility SDK of your choice and hit install. There's some small changes you need to make that I'll explain in a bit, but once you've made them, you're ready to build. This sample is one of our mesh shader samples on the DirectX Graphics Samples GitHub repo. It showcases mesh shader-based culling, which is also the technique that 3D Mark uses in their mesh shader feature test to get huge performance wins over the traditional geometry pipeline.
Oh yeah, this was like, what, 8 to 20 times faster geometry
showing how individual meshlets within this meshletized dragon get cold in the amplification shader stage before they get fed to the rest of the pipeline. This kind of culling is not possible with the traditional geometry pipeline, and done well in Engine has big perf implications. Okay, so even though this sample was pretty cool and also looks pretty nifty, we did talk about mesh shader-based culling at last year's DirectX Dev Day.
Yep,
this sample that. And our other mesh shader samples, courtesy of Matt Herleman, have also been up for some time. So why did I pick this sample in particular to show you? Well, those in the audience that have been following our work closely will know that mesh shaders is one of the more recent features in the DirectX 12 Ultimate feature set. In fact, they're so new that they only ship with the May 2020
Pascal
update.
Too.
Before today,
it had a good run.
If you wanted to run this sample, you'd also need to be on this pretty new OS.
Well, I guess it still lives on in the Switch to an extent because the Switch is a hybrid between
this machine that I'm running the sample on
Pascal,
is running on Windows version 1909, or the November 2019 update, which is an earlier OS. That's right. What I'm showing you right now is how the Agility SDK lets you light up newer DirectX 12 features than what's shipped in box with the OS. This used to be impossible before the Agility SDK.
Wow, great demo, Jacques. Before we talk about the code change you want to make, let's quickly talk about the contents of each Agility SDK. Each SDK contains the D312 core that a developer will include app local with their app, as well as the components needed for devs to build against the included D312 core. These are the API headers for the runtime, the debug layer, and D3 config. Earlier, I talked about requesting a newer D312 core than what's in the OS, i.e. the D312 cores that we're shipping in each SDK. So games set the needed parameters by exporting constant data via well-known symbols, which is what our loader needs to make its decision about whether to load an app's local copy of D312 core or to load the D312 core
like I've been pushing for, your full PC graphics settings will be available in console games.
You might export these constants via
honestly,
a module definition or a .def file.
We can't have them, even on the Switch.
That,
I mean,
you'll also want to declare D312 SDK version and D312 SDK path in code.
Hey, did I miss anything interesting?
Right here.
Well, they just we're talking about
to go over
DX12 Agility
SDK,
which is
I'd like to note that if you don't want to use the modular definition file, you can also use the deco
widespread full support for DX12
We'll call out
Ultimate.
both methods in our getting started guide.
Third-party devs will not use the full power. Yeah, that's a bummer.
For our first Agility SDK, D312 SDK version will be equal to 4.
Is like
Today,
these things
this
like
number
DX12 Agility
exceeds
SDK
any of the D312 SDK versions of any of the inbox System32
how
D312
Microsoft is trying to address and trying to push
until the next OS
ships
ships with a more recent D312 core.dll that has a higher SDK version. Our loader will always load the D312 core that we
Matt,
shipped
you didn't miss really anything terribly interesting, I think.
As mentioned earlier, developers must include
there were some
the D312
interesting new insights, I guess, on the sampler feedback demo, but
D312 SDK path is the path
we hear anything about DirectML
they use relative to their
no idea.
Here, the developers shipped it in a folder called D312.
I looked all over
right
the
next to the
Gamestack, like
you can see it in this little file
there was nothing about DirectML.
So,
I don't know.
we just covered what you need to do to build and ship a game using our new SDKs.
I didn't know.
I wanted to add one last bit here.
We'll go to like 25%.
After adding support for the Agility SDK to your engine, we recommend that you still query check.
Sorry, my mic might be here. I'll do half, but I think my mic just got pushed away from my mouth.
Even when
like I said, my mic is kind of junk.
It's still good practice to query check features.
I didn't say they.
Double check that the features you're trying to
hear they say won't force. Of course, they're not going to force anyone to, but I mean.
You will only get
from the sounds of it
result if everything, software,
I don't know why
drivers,
you wouldn't want to.
and hardware.
Yeah, it's perfect. Yeah, sorry. It's just I must have bumped it with my hand.
This is no different from how
knocked my mic away from my mouth.
If you were in the habit of using it, please carry on.
Like I said, crappy mic.
At the bottom, we see a developer checking if feature level 12.2 is supported. With the new Agility SDK you can download today, this H result will be SOK on any
That's
machine
like that
with the
909 OS or feature level thing. That's the one line of code I had to comment out in one of my classes that I'm like waiting for either it to reach outside of Windows Insider builds or now
which includes the full DirectX
12 Agility
feature set.
Like I'm so glad that I'm going to be able to like be done with that class now.
To wrap this all up, major developers have already gotten started with using the Agility SDK, and we're opening up the floodgates to all developers today. You can do the same. All this information
major developers
is readily available.
Using the Agility SDK to let DirectX 12 Agility. Well, I will definitely look into that if it's see if it's what is right for Void 2D and Void 3D because that sounds very exciting and
latest Agility SDKs will live.
Sounds like it might be what I'm interested in.
Please check out our DirectX Discord server. It's for developers of all skill levels. This Discord server is a great place to give us feedback, and please keep on doing so. It's literally because of developer feedback.
Didn't know you had a channel. Yeah, I don't post much on feature level 12. Do Series X, Series S,
to make the Agility
Ampere, Turing, and RX 6000. Yep.
And with that,
don't forget the rumored Switch Pro /2.
Before I hand this off to Q&A, I'd like to give
I'm just teasing.
Shout out to Randy Tidd, Seb Mary, Kev G, Sean Hargraves.
Sounds like major devs are using it already.
For all their dedicated work
yeah, sounds like it.
Made today's announcement possible.
All the first party, I'm sure, have already. Yep. I think when Bethesda said that it was like their biggest engine overhaul and that the Xbox was designed for the like data streaming in large worlds, I think that was kind of a little hint that they were like, we're going to do sampler feedback and we're going to do you know, DX12 Ultimate Discord. Yep, you can join the DirectX Discord. It's a good place. Oh, right. Hold on. I need to. Oops. I don't even want to replay it. All right. So, okay. I got a quick check one. Okay. Next is HLSL shader model 6.6 or direct storage for Windows. So sound off in the chat as to what you want me to stream, and I'll try and go with what the majority interest is. Again, so we can either do HLSL, which is the shader language for DirectX, so shader model 6.6, or direct storage for Windows. Direct storage for Windows. All right. Anyone else? Oh, we got a new dev blog up on the DirectX dev blog announcing the DirectX 12 Agility SDK. Shader, there's a couple people saying shader, some people saying direct storage. Let's see if there's anything new on. Yeah, it seems like Halo Infinite's going to be using that Agility SDK, considering that one of the guys at 343 said the DX12 Agility SDK allows if it's 343 to be confident the latest innovation from the DirectX team runs on nearly all of our PC players. I'm sure that they're also using this to scale across Xbox One and the Series X and S. So that's good news. So yeah, both at Turn 10 and Playground are going to be using DX12 Agility in Forza Motorsport and Forza Horizon. Agility SDK is not just great for PC gamers, of course. Xbox will reap the benefits. Good stuff. Direct storage. All right, I think we're gonna. Looks like more people are saying direct storage. So that's in about 15 minutes. Again, you can hang around here if you want to. We'll say this was good. You know, feel free to ask any questions you want. Oops. And you know, whatever. We'll go back to the stream in about 15 minutes. And I can go check my social media now. Ugh. Coof coof. What's this? Oh. I'm actually going to see if I can find their YouTube channel. I wanted to see if they are uploading things. No, so it seems they haven't uploaded, at least yet, the stuff on demand to their channel. Okay. Sorry. What's on the agenda for today's talks? Well, hold on, let me pull it up. So we'll do direct storage for Windows. That's what I'm streaming. There's also simultaneously the HLSL shader model. After that is what's new with high dynamic range in DirectX games, denoising ray trace soft shadows on Xbox Series X and S with Windows with Fidelity FX presented by AMD, and then finally introduction to real-time ray tracing with Minecraft presented by NVIDIA. Hey, Curb Sauce, are you going to be on RDX tonight? No, they haven't asked me to yet, so, I mean, I can be there in the chat and talk to people about whatever, but I'm not actually going to be on the panel currently. By this point in time, all of the first-party shooters should have the Agility SDK, yes. Wondering about those other major developers. I mean, it's probably going to be just like the rollout of the early GDKs and stuff, like the like we saw early on, where like your idea, like a specific number of IDA Xbox partners, probably most that are like going to put on games on Game Pass, as well as let me think, as like the really big third parties are going to get it first, and then it's going to trickle down to the mid-sized companies, and then last people like you and I or ID at Xbox now can get it today, but I suspect that a few other larger developers have already had it for a little bit. So when UE4 is supporting the oopsies, can Dell implement DX2 features usually? Because right now UE4, I don't think it'll be UE4. That I don't think UE4 will support DirectX 12 Ultimate. I think that's going to be Unreal Engine 5. Like obviously, like the Coalition's fork for Gears 5 was tuned to have Tier 2 variable rate shading, but that's like their own fork. It's not part of the main one that Epic Games maintains. So yeah, I think that Unreal is you're going to have to use Unreal Engine 5 for DX12U. Right, 10 minutes. Probably, yeah, yep. UE5 later this year. Yep, Epic said it's going to be public released, hopefully, with the COVID delays and stuff. You never know, but it's supposed to come out for public use in fall 2021, including the full source code, they said, for anyone who registers as a developer with Epic to, partner with and download and modify and contribute to. So that's fantastic in my opinion. I'm a big lover of open source software. You're going to watch direct storage. Yep, I'm going to stream the direct storage for Windows next. Because for the two sections where there were two at the same time, I just kind of did a informal vote in the chat at what people were interested in, and they chose that over the shader model 6.6. But after that, everything is actually there's no conflicting or overlapping times. It's HDR and then denoising, ray trace off shadows with Fidelity FX by AMD, and Minecraft introduction to Minecraft ray tracing by NVIDIA. Can we watch Xbox Series hardware innovations talk? I already. So how about this? It's the next talk, the direct storage for Windows, is about to begin in 7 minutes, and then after that, there's a 10-minute break before the HDR talk. However, after that, there's at 2 Eastern, there is a 50-minute time gap, which I can go back and show the Series X hardware innovations video to anyone who missed it, which actually I don't think I was streaming it before. So yeah, so we definitely can go do that, just not like this instant. It'll be about an hour from now that I'll go go back and play that again. Boy, oh shoot, I almost bumped my mic away. Thanks. Yep, no problem. I just I don't want to like be breaking it up because that it's gonna be easier for people to follow if they can just watch it in one sitting. So many events today, like Apple event is about to kick. Oh, right, the Apple event. Oh, well, you can't catch them all, I guess. Or you can if you're playing Pokemon. All right. Got less than 2 minutes to go. Let me go move to our direct storage for Windows. Refresh. Nice. I gotta turn the volume down again. Hold on. All right, here we go.
Hi, so I'm Andrew Young on the Microsoft Graphics team. You can kind of tell from the shirt. My GSL shirt says Build Better
Captions again.
Shaders. And today I'll be talking to you about direct storage for Windows. So why don't we just jump right into it? Here's a little bit of an agenda. It'll be a direct storage for Windows update. Last year we had actually
Why would you talk over the stream? Because I
give you a little bit more
detail
about how it works.
Said that I would be open to conversing with
people. We're going to talk about the context of the journey to eliminate load time, something that nobody really likes.
I have the captions on for people who want to, see it.
We'll talk about
who want to, if for people if you miss
how it's the next big step to eliminating those load times and a couple of other scenarios. And then we'll talk about how to start building a direct storage ready engine. It's a paradigm shift. There's going to be some changes to your engine, and so we want to give you an idea of what that looks like. So let's start with the context. We want to give you a little bit of an idea of why this is a problem in the first place, what kind of experience users get, and how we want to go and make that better. But first, let's talk about how hardware fuels gaming innovation. And so in the hardware space, there's basically constant competition to continue building the best gaming hardware. And that will basically feed innovation into gaming experiences. In some cases, you might want to improve. 1 year, the industry might be trying to improve resolution. Another year, we might be trying to improve frame rate, go from 60 to 120 or from 32 to 60. And in this case, we also see hardware being innovated on to provide improved load times. And so we want to be able to take best advantage of that. And so let's take a look at a couple of examples. You have components, you have the evolution, you have processor speed.
Yeah, I mean, like I said, if you really want to, I don't mean to be a jerk, but if you really want to see just a a stream without any commentary,
VRAM has gone from kilobytes to megabytes to gigabytes,
then you honestly should have gone and signed up for the event yourself, because it's completely free and open to everyone. I mean, come on, guys.
And so we have to ask ourselves, well, IO tech has improved a lot, just as any kind of piece of hardware improves. That doesn't necessarily mean that the experience itself will improve. And so what we see today is that IO tech has improved quite a bit, and yet we still get these experiences where you only have a short time to play, especially in the pandemic right now, where you might want to just get in 15 minutes or 20 minutes of gameplay, and a lot of it's just loading times. That's not a very good experience. Another one, which I've encountered a lot, maybe I should get better at playing games, is every time I die, let's say you're 5 seconds.
Eliminate load times by getting good.
You get to the boss, you die within the next 5 seconds, so you've played only maybe about 10 seconds, and I have to wait another 20 seconds, 30 seconds to try again. Also not a very good experience, not something that I want to spend my day doing, just waiting. Another one, this is not really a load time related one, but we do see this today in modern games still, is when you fast travel, when you go from point A to point B, and you load this new area of the map, sometimes it looks like you're playing games in the 90s again, or the 2000s. If you remember, you have a character with a face that doesn't really exist. It's just a block. And then it starts popping in, and you have all the trees in the background. They start popping in. That's not a very
pop-in is the worst. I was
jarring.
I'm playing Sword Art Online Alicization on my Xbox right now, and the engine they use is just not very good. The pop-in is like,
but you kind of walk into an elevator in a game, and you're trying to, and the elevator serves as.
Did the Game Pass session go live yet? I honestly have no idea, because I'm interested and signed, like put on my schedule.
Waiting for it to change, or
doors to open. All like the tech and graphics stuff, because that's just what I do.
It's basically an elevator simulator, and again, not a very.
I mean, I can quick check for you.
So we got to ask ourselves: are we really utilizing the hardware effectively in these experiences? I shouldn't say experiences. If these bad experiences exist still today, even though IO tech has improved, are we really using it effectively? The short answer is no. IO hardware has evolved really, really far in the past little while, but it's beyond what software can accommodate. So there are a couple of bottlenecks, and we'll talk about those in a bit. But it essentially prevents it from getting the maximum potential out of that hardware. So let's take a look at an example. Let's say you're moving from a hard drive HDD. A user is moved from an HDD to a NVMe SSD.
Pop in. It's good. Yep.
There's a huge leap in IO capabilities. We're talking 40 times
Yes, we need
faster
Kirby Insights too.
on
That's why you're here.
Yep.
I don't see any Game Pass sessions, Death Singer. I'm sorry. Maybe I'm just totally blind or not looking in the right place.
Improvement on PC games if you just swap out the hardware.
I mean, in the opening keynote, I think Phil and Sarabon talked a little bit about Game Pass and how it's great, but
times more faster hardware and only get like
I don't see like a specific Game Pass
that would take advantage of the full bandwidth. How
session. Sorry.
Is that there are several factors. CPU bound is one of them. The paradigm that we're using to actually load the textures in or other assets is another one, and it boils down to essentially taking too much time to load too much data. And so how do we get down to that under 1 second load time North Star? That's where we really want to go, where it starts feeling instantaneous.
Yep. You see where it says CPU bound here? I want to point out that if you go back and watch the original, the GeForce RTX 30 event, when they get to the section on direct storage, Jensen talks about, like, he has this diagram up, and I think I forget exactly where, but if you just search RTX IO, you should find the link on NVIDIA's website, where currently, like, the CPU has to funnel like, it receives all the data from the NVMe, and then it has to funnel it over PCI Express to your GPU.
How much data
under direct storage,
and Y megabytes per second.
And of course, this causes a CPU bottleneck. So under direct storage, the GPU itself is able to get data directly from the SSD, which reduces the CPU load and improves performance, which is another great innovation. So yeah, if you want to know more about this, you should definitely go rewatch the NVIDIA RTX IO talk. Or section, because it is definitely good.
So by doing that, minimizing X or maximizing Y, you can.
Did they talk about Project Tiger? Project Tiger Cat is something I'm doing. It's nothing to do with Gamestack.
Smarter, to help your smarter.
That's my equivalent to the Digital Foundry tools or TR Drop.
Both of these already exist on Xbox.
That's going to take a while because
PC, and we're bringing direct storage as well to PC.
It's tricky. Just kidding. Oh, okay, you got me there.
So today we'll be talking specifically about direct storage. At the end, we'll talk a little bit about how sampler feedback and direct storage kind of combine together to give you a very, very modernized engine, which allows you to transfer all that data pretty quickly and only what you need. So now is probably a good time to remind you that we're always in the business of helping you maximize the potential on both Xbox and PC. The Xbox Velocity architecture, if you've read about it, it lets you get the most out of your console's cutting-edge hardware. It includes sampler feedback, it includes direct storage, and console being a single piece of hardware. Actually, there are two. All users will, a Series X and S consoles will benefit all at once. Now, on PC, the story is a little bit different. PCs aren't all the same. But we still want to enable you to get the most out of the available hardware, and that's what these features aim to do.
NVMe prices drop. Clearly, this was made before the whole shit show with GPU pricing, because NVMe SSD pricing is no longer the main worry.
Another example relevant to us in this particular talk is NVMe SSD prices drop. And what you see essentially is a sudden but not instantaneous shift of users to NVMe SSD equipped PCs. But again, not everybody has it all at once. And so what we strive to do with the DirectX platform, and what we're doing with all the features, is one, converge DirectX platform.
Future innovations. I wonder what that could hold for us.
On both console and PC. We make those cutting edge features available where the hardware makes them available. And that is true on DirectX 12 Ultimate. It's true for direct storage, and it'll be true for future innovation. All right, and so let's get into the details of how direct storage actually works, how it's built, and how it's going to help solve the load time problem and texture streaming problem that we kind of called out before. We can start with an overall architecture. Here on the left, you can see kind of how it breaks down. The goals and design principles for direct storage are the same as Xbox. The APIs are very similar, with only minor differences. It's kind of similar to how DirectX, D3D 12, I should say, is the same or very similar on Xbox and PC.
Sorry, I was looking at something else.
And then
application,
the
direct storage,
will of course differ. The underlying technology, how you deliver the functionality for the API will differ on PC versus Xbox. Although your developer experience in the application is
so basically the nitty gritty underlying stuff isn't exactly the same between Xbox and PC, obviously, but it's still a unified programming model for the API.
That's the component that your application actually talks to. It's the way that we abstract a little bit of functionality while giving you control over the hardware.
Which is, good.
Pretty direct control over the hardware.
We don't have to worry about the little details that will be handled by Microsoft, AMD, and NVIDIA.
You have the asset decompression piece, and we'll talk a lot more about this in a detailed
slide.
Sys
requirements, please. Well, I believe
the Windows Storage Stack. Windows Storage
either an Xbox, a NVIDIA RTX, so either Turing or Ampere, or an AMD RX 6000.
The destination, either CPU access or the GPU.
I know, obviously, NVIDIA confirmed Ampere will support it, and then there were some questions if, is Turing going to support it or not, and I forget where the source was, but I promise you I'm telling the truth, where someone did figure out that, yes, Turing will support direct storage.
Let's talk a little bit about the scenarios.
They just didn't talk about it because the presentation was about Ampere.
So we talked about the end-user scenarios, but how does this look like from a technical perspective? What are the technical scenarios that back those experiences?
They confirmed Turing support, which is great because I'm honestly not interested in upgrading right now. I think I'm going to wait for the 5-nanometer architures.
The destination is GPU. That can be geometry, textures.
I'm just happy with my current PC, so I don't see why I need to upgrade.
That one out. We also have to remember that we have situations where we want to copy data that's destined for CPU usage. Like they don't go over the bus to the GPU or
maybe,
RAM.
Obviously, maybe some people who might not have the system I have, they might want to upgrade their rig, and of course that's good for them. I mean, that's kind of the big pillar of PC gaming is customization.
So you have to consider the situation where you have to
I'm just worried if Direct Storage needs a PCIe switch or something else. Oh, I have no idea. I've never heard anything about that.
But then there's a secondary wrapper of compression around that.
Or specific NVMe SSDs. I think it'll work with anything that's PCIe 3.0.
BC format texture wrapped by another decompression to make it disk space optimized.
That would suck if it did require PCIe Express 4. I have a PCIe 3 NVMe right now, and I do have Zen 2 plus X570, so I could upgrade to Gen 4, but
can use it to render the scene, etc. And so
I don't think that would be worth the money at this point. I mean, my NVMe SSD I find works really well. Hopefully they'll clear it up. Yeah, I hope.
The inner BC compression.
And so I can hear. You know what I'm going to do? I'm going to go ask them a question.
What does it look like from point A to point B?
I'm going to have to minimize this for a second here. Sorry, guys.
Data, of course, starts on the NVMe SSD. The user had downloaded their game. The game package is on their drive.
Well,
First thing we need to do is to get that data off the disk. And so we have a storage read using the existing storage stack, Windows storage stack. You get into system memory. That's RAM. And then at that point in time, a game will have to decompress this asset. And so they use CPU decompression. You decompress it, goes back into system memory. And then for GPU related textures, again, we're focusing on textures just simply because that's the most complex path that we have to consider. Then you have to copy to the GPU, at which point it can be used finally. So that's today.
Yep, that would be great. Well, I just sent the question in. Their mod's going to have to approve it. I'm sure they will, but we'll see. Let me go. And now back to full screen.
You have the NVMe SSD with the game package. You do a storage read of
also ask if it already works on existing laptops. Okay, hold on.
That would go to the optimized storage stack. Again, we'll talk about that a bit in a detailed slide. Goes to system memory. But at this point, you're not going to do the decompression. What's going to happen is you're going to just do the copy directly to the GPU first. So you do copy to system, copy to GPU, and only then are you going to do the decompression. And so a couple of reasons why we want to do that. One, with the right decompression algorithm, the GPU actually supports far higher bandwidths for decompression, key for both scenarios of texture streaming and load time.
Direct Storage will support PCIe 3 NVMe SSDs. Yes, that is great news.
So we're talking gigabytes.
Don't have to upgrade.
Are really, really big.
At least I don't have to for my desktop. And I said, and then yes, I asked also will it work on existing laptops with the GPU architecture that support direct storage, such as RTX 2030 or RX 6000. Thanks, excellent. Yep, I know. I'm very happy because I love my Intel 660p. It is such a great bang for your buck PC part.
A drive that's capable.
Like I've called it before, the workhorse of the NVMe drives.
Maintaining that.
It's not the best in the world, but it gets the job done without breaking the bank. You are doing God's work. Oh, thank you. That's so nice. Oh, shoot. Let me go back to full screen.
Completely offloading the CPU for any GPU destined assets. The data is actually
honestly.
Its destination.
It's not terribly surprising to me, considering what they just said about Agility DX12 and supporting a range of features.
When it's
oh, the Kirby Stream test stream. Oh yeah, thanks.
You only have to copy 1 megabyte over to system memory, and then you copy 1 megabyte, not 2 megabytes, to GPU, and then you decompress it. You expand it out to 2 megabytes.
Yet. No reply on the laptop question.
1 megabyte first to system memory. You decompress it, then you're copying 2 megabytes over the PCIe bus or into GPU accessible memory. And keeping it small to the very end actually makes you more efficient. You're using less bandwidth when you until you really need it. And then finally, doing this actually opens up the door to other optimizations that we can implement. I won't get into too much detail there, but there is an evolution to direct storage that we can look forward to. All right, so let's get into the details of each individual component. You have the direct storage API. It's essentially the newest addition to the DirectX family of APIs. There's D3D. Direct storage is just another direct branded API. It integrates directly with D3D12. essentially bridging the gap between storage and GPU technology.
Hopefully they won't over. Yeah, I know. Yep, I hope to. With 343 using agility, I wonder how many features they've been able to implement for Infinite. So they already said that they were implementing variable rate shading. I'm assuming that's tier 2 because that's the good version of it. Ray tracing is going to come, they said later, obviously, assuming DXR 1.1 as well there because of the performance gains. And they said GPU-driven rendering. That's a little less clear. I think that might just be GPU scheduling for DXR 1.1. It could be something else, but I doubt it. I think they're just going to go with Tier 2 variable rate shading in DXR 1.1, at least from the start. I mean, they said, what, Halo Infinite's supposed to be like 7 to 10 years or something? Or no, it was 10 years. I'm confusing 7 to 10 with the Switch's lifespan. 10 years. So, I mean, obviously they could update it a couple years in the future with more DX12 Ultimate or Velocity features. But I think early on, you're just going to see ray tracing and variable rate shading.
Or notifying components when they really need to be notified, and that essentially becomes a batch workload.
I gotta go back
in the
to
past,
hold on.
You might have seen games, you load the entire thing and then you go. Now we get down to the granularity of textures, and then now we get down to the granularity.
Yeah, apologies if I've missed something.
Further down to the granularity of tiles.
Just I'm multitasking is not the easiest thing in the world, even when you have a nice big screen. We should figure this out this month's Inside Infinite. PC Deep Dive is... Oh, that's good news. I mean, the first Halo game I played at our computer club was a pirated version of Halo 1 PC. That was all. I mean, I didn't really understand kind of what Halo was at the time, but I know I had a hell of a time playing it.
Storage essentially introduces that same batch model, or it introduces a batch model, the same idea of leveraging the parallel behavior of the system and hardware. It applies that batch model to storage read requests, and it also bridges the storage stack with the GPU in a very, very efficient way. And that helps us maximize NVMe SSD performance, and also helps us remove any loss in efficiency between basically connecting those two subsystems together. An example, existing I/O APIs essentially treat every request individually. You have to make one request and you get a completion notification for one request. It's analogous to drawing one triangle and it telling you when you're done one triangle. In this case, it's you make one request for a piece of data off the disk, and then you get a completion saying it's done. That's super, super inefficient, especially if you have a large number of requests, like hundreds, thousands, even tens of thousands of requests per second. You don't really want to be doing one at a time. So the Direct Storage API essentially allows you, the developer who's building the game, to create these batched requests and to identify when you want to be notified. If you have, say, 1,000 things that you need, you can say, I want these 1,000 things, and only when those 1,000 things are done do I want to be notified. It significantly reduces the application paperwork that you need to do to make sure that there's a lot less overhead overall.
Yeah, this paperwork or busy work reduction is devs are going to love that.
And that's asset decompression.
And it's also great for gamers because less time on minutia means more time on the important stuff or optimization or,
pushing the hardware to the limits.
That woman must be exhausted. I wonder if direct storage will get much use considering the size of Infinite's map. I had it pegged at 84 square miles. That's interesting. I'd like to know how you came to that number. Plus, there's underground sections.
And so these asset packages are really, really big, and they're compressed to fit on disk. They are decompressed at runtime, and so it's not like you're downloading, say, a 100 gigabyte package. You decompress it to 150 gigabytes or 200 gigabytes. The user doesn't really want a 150, 200 gigabyte package on their disk at all times. And so what we really see is the evolution of decompression technologies that decompress assets before you need them in the game while keeping them compressed on disk. And so there have been specialized CPU-based decompressors that were created for this exact purpose, for gaming purposes. But at the very high rates of today of NVMe drives and just the system overall, like PCIe Express, decompression overhead is getting really, really expensive to maximize the potential of that hardware. So gaming has created the need for us to innovate in that space, but we really do need to make another leap. And so we need new innovation in specifically compression, decompression technologies. And so Xbox Series X and S, they have hardware accelerated decompression. That's part of the velocity architecture. That's one of the pieces to decompressing the assets.
Did they respond to the laptop question? Oh, I'm sorry. Let me go check. I'm kind of
how do we really accommodate?
Did they respond to the laptop question?
Silicon being in this case
existing hardware with NVMe SSD and DirectX 12 capable GPU compatible with direct storage. Yes, iGPUs and DGPUs. So they didn't like exactly address it, but from what it sounds like, your laptops with DX12U, or possibly even just DX12 in general, GPUs will be able to support direct storage on PC, obviously, barring driver support. I'm not sure if it is something that can be supported by non-DX12 Ultimate GPUs. I'm not sure if AMD or NVIDIA are going to go back and add in driver support. But from what it sounds like, the laptops will support it. Yeah, sounds like that's great news. Yep, I agree. Check the Xbox fan Discord. I had people's previous numbers in my own math. It's possible to calculate. There's a waypoint visible in the frame. Okay, cool. I will do that later. I got to go back to full screen.
Making a compression technology GPU friendly, as it were, requires innovation in how the compression technology actually works. You don't really have to worry about that, but there are 3 components under development, essentially. There's a direct compute based decompressor that essentially allows us to run it on existing GPUs. There's an initial prototype that we have. It easily saturates gaming SSD bandwidth, and so we're pretty confident, we're pretty happy with the results and being able to enable you, the game developers, to take advantage of the full bandwidth once we're able to release direct storage. This also opens a door to further innovation. Just because hardware isn't available today doesn't mean we don't want to find a path to hardware. And so while we have a direct compute-based decompressor for bootstrapping and giving you something to start with to get those higher bandwidths, we do want to make sure that we enable hardware implementations in the future. There's a CPU decompressor for assets. Like we were saying, a lot of the assets are destined for the GPU, but not all of them. And so we do have to provide a CPU decompressor for assets destined for system memory. Audio was an example.
Microsoft GPU vendor collaboration created a GPU compression system that works on today's GPU hardware. Nice.
As well.
Give that lady some water, Microsoft.
This package will be part of.
I should get some water myself in between.
Package that will deliver
session and the next,
so you can take advantage of this technology. So let's take a look at the Windows storage stack. This is the last of those 3 components that I mentioned before. What we're basically doing here at Microsoft is optimizing Windows for high bandwidth and high IOPS direct storage scenarios. It's important to recognize that it's not just high bandwidth that you want, but because of that very highly granular and parallel workload, there's also a high number of IOPS. And so you can imagine your game, you have extra streaming, you have tiles. Those tiles are small, but you want to have a lot of them loaded in at once. We have to essentially make the system efficient for many small requests. We're not just optimizing for a single, many gigabyte size file. There are details around why. And so we're achieving this by optimizing path length and reducing CPU usage. The I/O stack bypasses certain parts of the Windows stack. Windows will bypass certain parts of the I/O stack in this situation. And we're reducing user mode and kernel mode transitions. And
just wanted to say with this, if you need a more layman explanation,
OS improvement. You don't really have to worry about it.
Believe it's either on the Linus Tech Tips or the Tech Wiki channel. It's a video called something like "How a Console Could Beat Your PC" or "Direct Storage Explained," and they give a more simplified explanation of direct storage and how it's making improvements related to that. So. If anyone's still confused from the kind of high-level tech nerd terms they use, recommend you go watch that.
Recently, and that's essentially increasing faster than VRAMs increasing on GPUs. You see games, they are 10 to 50 to 100 gigabytes in size. VRAM is not going from 10 to 50 to 100. The increase in VRAM is slower. And so we need to accommodate that. And that essentially demands that the game become smarter and faster. There are memory multiplier techniques that are very powerful.
Yes.
This allows, boils down to being very selective with your data, and using sampler feedback can do that while having very, very fast asset turnover with direct storage, since you're going to be bringing data in and
direct
out.
Storage really does seem like the game-changing feature out of everything. Yep, it's definitely one of the cool features.
As much data as you needed to before. Let's say you have 5 megabytes.
Makes it look like your GPU has X times more memory than is physically available. Yeah,
really looks like
that's going to really help cards like the 3060 Ti, 3070, and 3080, which, well, the 3080 a little less, but like those cards don't have the most VRAM in the world compared to, say, the RX 6800 XT and 6900 XT. Which isn't, you know, I mean, it's a lot of VRAM is, it's a nice thing to have.
As to where you want that high detail.
But it's not the end of the world because of this tech, which is great.
Amount of hardware. And so you can start building for next gen basically right now. You should start re-architecting your engines for this kind of very granular and parallel workload, your PC engines. And you can start by integrating sampler feedback. Right. First thing you want to do is make sure that you are selective about that data.
New iMac and Apple TV announced. Nice. Is Apple Silicon iMac or like the last of the Intel iMacs? Maybe the 8K thing outside the Series X may not be a joke in the future.
I will also mention.
I mean, yeah, the 8K DLSS 8K on the RTX 3090 is very real. I mean, obviously it's a bit of a limited use case because of how expensive that hardware is, but it is a thing.
It's actually Ask Windows Direct Storage. Pretty easy to remember. Ask Windy Storage, with your name, email, and studio name. If you're interested in participating, we'll reach out to you. If you're
all right, so I will reach out to them.
You can, of course, get updates on our blog.
I'm not no guarantees I'll be
One thing
chosen,
I also
but
really want to mention.
We'll try.
We are very thankful for our collaboration.
M1 chip, Apple Silicon. Okay, M1 iMac. So I'm assuming it's clocked a lot higher with a lot higher TDP.
Are passionate about. And doing so in a very
hopefully that brings some monster performance.
To the DirectX family of APIs. And so
is it M1 or M1X or M1Z or? You know, like
here's a little bit of helpful reading.
A special variant of the M1 or just good old M1 like we know it in the
get it into the feature
in the MacBooks
and
the Mac Mini.
I will thank you for listening to this talk, and am excited to see all of you build your engines for direct storage and next gen scenarios. So thank you, and have a great rest of your GSL conference.
All right. Okay. I am going to now. That's good. So I'm going to go grab some water, and we'll be right back because the next session. Let me just double check. Hold on. That's not what I wanted. The next session is at 1:40, so yeah, I'll be right back. All right, I'm back. Let's see, anyone posted anything in the stream chat while I was gone? Very nice. It's just a M1. It's also very thin. Well, I'll go check it out in the meanwhile. I'll have a minute here. Oh man, am I ever glad that I chose to get my my this week's homework done ahead of time. On Apple unveils iMac redesign with M1 chip built in-house. I see. Oh yeah, that is one hell of a thin iMac. And it's got like that the old school like thing they did with the bulky one with the CRT, like the color scheme thing. All right, cool. Well, hopefully it's clocked a lot higher since it's larger. It's also very thin. Yes, it's beautiful and fresh. Yep, yeah, that's what I was thinking of. The G3, I think. It's either G3 or the G4. Let me look it up. iMac G. No, not the G4. It's a G3, right? The iMac G3. We used to have one of those, and yeah, I used to play like educational kids games on it all the time. Man, we had like the original version of it, ATI Rage 2C with 2 megabytes of video memory. How far we have come. Yeah, G3. Why don't games have full real-time water simulation using machine learning? Even just PC games, NVIDIA did real-time fluid simulation 7 years ago. Probably developers just don't want to implement it, is my honest to God guess. I mean, it's not that the tech isn't there. You could probably do fluid simulation without a GPU that can accelerate ML. Let alone with one that can. But good. I just think that devs didn't want to implement it. I think so. Naughty Dog will do it because why? I think what was it? Red Dead Redemption 2 on PC. It was a pretty taxing setting, but if you turned like the water quality or water simulation all the way up, it wasn't machine learning based, but it was a pretty high quality water simulation. So I guess there's one thing. They use particles for Last of Us Part 2. That is true. Okay, let's see. I'm going to pull up the next thing. So, next up, what's new with high dynamic range in DirectX games?
Hello, Gamestack Live.
Oh, wow.
Wherever you are in the world,
Overwatch.
welcome.
Man,
it's awesome to be here with you today, even if it's only virtually. Of course, whilst you're watching this video, it's probably raining outside here in Seattle, so maybe virtual is for the best. I'm Simon, and I'm a member of the DirectX team here at Microsoft. It's my privilege to talk to you today about how we're improving high dynamic range support in DirectX games. Now, this is a Windows and PC focused session, but most of the information also applies to Xbox, and many of our best practices can also apply to any cross-platform title. So we have a full agenda for you today. We'll start with a quick update on how ecosystem adoption is going with HDR in Windows.
Oh, yeah.
Then we'll dive
HDR
deep
PC
into the display hardware portion of that
it's
ecosystem.
Not in a great state,
looking at the
honest.
recent work
it's
that
getting
Microsoft
better,
is doing to improve the quality of HDR displays.
Honestly, like if you want HDR,
then we'll go into a lesson about
bet.
how your game can take advantage of Windows system
Auto
capabilities
HDR, of course, is going to be
and tune your content to optimize for a particular HDR display.
But also, display manufacturers.
And finally, we'll cover an exciting new technology, Auto HDR, that we recently announced. You'll learn what it offers to games and how you as a developer
make more balanced monitors with HDR support too.
Okay, let's dive in. So we first shipped HDR support on Windows 10 back in 2017, and we've come a long way. We've steadily enhanced support in the operating system, and we've been super impressed by the progress across our ecosystem.
Tad bit quiet. Oh, must have been my mic. Sorry, is that better?
PC manufacturers.
My mic sometimes gets bumped away from my mouth, and it's a crappy mic, so that happens.
We have games with over 130 titles using HDR in Windows. Just looking at games published by Microsoft, we see beautiful HDR across all kinds of art styles and gameplay genres, including Flight Simulator, Ori and the Will of the Wisps, and Gears Tactics. Moving on to hardware, we have over 250 certified laptops and monitors.
Yeah, the problem with that is that stuff like Display HDR 400 is it's honestly pretty shit. Like it really starts at Display HDR 600 for a
HDR capable PCs.
Passable HDR experience.
Has been growing by 3 times every year over the last couple of years. This means a PC meeting all of the system requirements to run HDR, including an HDR display and a GPU. Even more impressive is the number of active engagement hours. This has been going up by 4 times year over year. At the bottom, we have just a couple of
that one there that says those couple that say HDR 400, like
that were recently anned.
Avoid Display HDR 400 displays if you're buying a new PC display, and if you think you're getting like LG C10 or OLED levels, you're mistaken. You got to start at least Display HDR 600. Those Display HDR 400 ones suck.
But at the same time, we know that doing HDR the right way is hard. So I want to frame the rest of this session's contents in terms of the top challenges that you have been seeing and how Microsoft and Windows are helping. First, when we talk to developers,
of course, that does mean you're going to be paying a pretty penny because good HDR PC monitors don't come on your usually aren't available mid-range or budget.
To raise the consistency,
you usually have to spend like $1,000 or something.
When your game is actually running on a gamer's system, we'll teach you how to extract the maximum image quality from their display. And finally, we strongly believe that HDR is the new standard for any high-fidelity game. But let's say you're working on a game with existing engine or existing art assets, and the upfront investment needed to upgrade is just not an option. In these cases, Auto HDR provides a great bridge for your already shipped code to gain many of the benefits of HDR. All right, first on the list of challenges is HDR display quality.
Okay, guys. Yeah, Discord
for those of us who are immersed in the world
has exited HDR, talks with Microsoft for the acquisition.
For starters, HDR displays have a huge dynamic range of price and performance, no pun intended. You can have a budget HDR monitor that barely hits 200 nits of peak luminance, and this is no better than a traditional display. And it can sit right next to a
cheap
mini
budget
LED
HDR displays. I can't stress enough how much that you should avoid them. They really suck.
Yet both of these displays can claim to be HDR10 compatible. What's worse, once you try rendering to a display, it may do anything and everything to your color values.
Poor color reproduction.
I mean, distorting the hues.
I've never seen a TN
or any one of a number of possibly
HDR display, and obviously IPS has great color reproduction, and VA can, if you calibrate, you can get pretty close to IPS. Plus, IPS can also be calibrated for better performance.
So this obviously wreaks havoc with the color grading and artistic intent that your team has carefully defined, but can also break your gameplay. Imagine you're playing a competitive multiplayer shooter, and you're inside a building, and you're looking out a window at the bright sun. On a poor quality HDR display,
it's just pole white and
this
blown
is
out.
Clip the entire scene to white, and so you literally
when HDR
won't
done
be able
right,
to
it looks
see
amazing.
Your opponent who might be facing you with their gun ready to shoot.
There's lots of good HDR
and finally,
games
when
out
your
there
customers
that
or even members of your own studio ask what HDR monitor they should
There's
purchase,
also plenty
it's
that
really hard to
stink
provide
it
a
up.
good recommendation. Microsoft's approach is to partner closely with the industry to promote and develop HDR standards and certifications. This includes groups like VESA Display HDR, which will be the focus of this session, and the HDR Gaming Interest Group. We want as many manufacturers to be able to participate as possible, and therefore our specs and programs are vendor neutral and open. As I noted before, every major PC manufacturer and monitor manufacturer is building display HDR products today. Looking at the standards themselves, we were laser focused on designing them to ensure a high quality end-to-end user experience. On display HDR in particular, this means it requires accurate and consistent color reproduction and capability reporting. And this helps to guarantee your game's artistic intent and gameplay are preserved. Now, we also want to promote innovation, where manufacturers compete to raise the performance of their displays and provide users with a superior user experience. Here are some example display HDR performance tiers. Each tier defines a comprehensive set of image quality requirements.
You know, I
this
think
static
recently
contrast,
something
color
that's interesting
accuracy,
is
gamuts,
NVIDIA
but for
revised
they get a simple message. They look for
requirements
a higher number
for
as better.
G-Sync
The numbers
Ultimate
here
certification.
represent the peak
I
luminance
think
of the
the
display
LG
in nits,
C10
which is
and C1 and those
intuitive
family
measure of
of the
HDR
2020 and
performance.
2021
In addition,
OLEDs from
tiers
LG
like True Black
now,
showcase the
while they
strengths
didn't
of
make
OLED
the
and
cut because they
self-emissive
were
panel technologies. Their peak luminance
you know,
is
at
more
the time
limited than other
it was
tech,
higher, but I
they
think
offer
now they actually
superior
meet the
viewing,
G-Sync Ultimate
superior
spec.
image quality in dark viewing
So
conditions.
that's nice, and of course they are regular G-Sync compatible and FreeSync enabled. So
certified HDR displays will just work.
That's nice.
Of course, in the next section, I'll cover some best practices for your game to optimize for HDR, and also how to handle non-certified displays. For purchasing guidance, Microsoft strongly recommends consumers look for a certification like Display HDR. This guarantees you'll get a baseline of quality, and based on your budget, you can then choose a performance tier to match. Now, there are other HDR certification programs run by our silicon partners. This includes AMD FreeSync Premium Pro, Dolby Vision, and NVIDIA G-Sync Ultimate. These programs are great
just
too.
so you know, FreeSync 2, if you see like an older monitor that says it's FreeSync 2, FreeSync 2 is the same as FreeSync Premium Pro, so the highest tier of FreeSync, how it's classified today.
For a color grading or mastering display, we specifically recommend a Display HDR 1000, 1400, or higher tier.
Well, that's going to
cost you. These are capable of reproducing the colors from the vast majority of consumer HDR displays out there today.
You're looking at least $1,000,
so as I just
if not
mentioned,
more, for
even with certified HDR displays, we still have best practices
1,000.
you should follow to give your HDR game the best possible experience on the hardware that your gamers are using. HDR calibration on displays is a pretty deep topic. So I've organized this section into tiers: good, better, and best. Each tier involves incrementally more work over the previous tier, and in return, you'll get a superior user experience and image quality. Good, you're simply using the operating system APIs to get the calibration data Windows already has, for example, for a certified display. Better is about supplementing that data for displays that aren't certified, so you guarantee a consistent experience across every kind of display your users may own. This is especially important for HDR televisions, which are very common, and many of them don't follow any HDR certification. And finally, best is about providing the additional knobs and settings so you can extract the maximum image quality out of the user's display and specifically optimize for your game's content.
Exactly.
As a note, in this
this
section,
is why
I'm only going to give a summary of
should
our
have
full
all
guidance.
consoles, Switch
you can
included,
find more
should get
information
full
at the
PC
documentation
graphics settings,
in the link.
at least in some kind of hidden menu or idiot-proof thing.
DirectX
like,
APIs
come on.
to get access to the data
We
that
power
Windows
users are
has
not
about the
stupid.
user's
Stop
HDR
treating us like
display.
that. We are.
DirectX combines data from multiple sources, including EDID, display ID, color profiles, external calibration apps, etc. And it rationalizes them to give you a single best known data set.
Seriously, yeah.
For those displays that don't come with accurate data, we are working on a system calibration app that the user can run, and the data is then exposed via the same system APIs. This app has already shipped on Xbox and is coming to Windows. A critical concept that's particularly relevant to PCs is that your display's HDR capabilities can change at any time. This could be because your user has moved their game between different monitors, because they're on a laptop or another device with power saving modes, or even because the room has gotten brighter or darker, changing the viewing conditions. Use our APIs to detect these changes and adapt your game's rendering to the new state of the display. This adaptation process is called display mapping, or sometimes tone mapping. Display mapping is its own enormous topic, and our docs
I didn't even know you had a YouTube. When it comes to tech, I search for you,
HDR tone mapper APIs.
Okay. No, yeah, I mean, I don't upload a lot
let's
to
quickly
it,
look at some code
so
examples.
I'm not surprised.
There are two display capability APIs you can use.
Optimized games. Yes.
The first option uses DXGI and integrates directly into your
yeah,
game's
I'm not a
rendering.
fan of bad optimized games either, but I'm the biggest reason that I want to see graphic settings on console is just
you get
more freedom.
DXGI output.
Like, let me use my hardware the way I want to. When we have these so PC-like architectures, there's just no reason that we should not,
and color primaries.
Console users should not get the same options that PC does.
The second option is a Windows Runtime API. It's a little more flexible, but today it's only available for universal Windows apps. We provide an event handler called Advanced Color Info Changed. You implement your event handler and then grab the Advanced Color Info object. And from there, the same information is available. Okay, let's move on to better. This guarantees that for any display, whether it's calibrated or not, your game still has access to the most important subset of display color information. That subset is what we call the safe luminance rendering range. To help explain what that means, let's look at this diagram. I've plotted out a bunch of measurements from an actual HDR display. The x-axis is the luminance of the color values your game is rendering, measured in nits. And the y-axis represents the photons that the display is actually outputting, also in nits. As you can see, the relationship isn't linear. There is a minimum and maximum point at which the display just can't get any brighter or darker, and so it saturates or clips your game's colors. So your game needs to restrict its rendering to this safe range and never exceed the minimum and maximum luminance. Here's an example of a simulated image of an outdoor HDR scene that visualizes what clipping looks like. You can see in the upper left corner, we've lost all of the details in the sun and clouds. Similarly, in the lower left corner, we've lost detail in those rocks. Let's show you an example of how to implement basic calibration. This is exactly what our system calibration app is doing.
Well, I think
as I mentioned earlier, it's shipping today on Xbox One and later,
casual gamers,
and we're working on bringing it to
Yeah,
Windows.
I know, which is why I'm saying, like, I'm willing to make a compromise, like if they were to do that, like, hide it behind some kind of quote-unquote idiot-proof thing, like with warnings and a reset to default option and buried in the menus, but
100% frame.
You know, even if it's just that, even if I'd be totally willing to go through that to get it. Let me play War Thunder at a stable frame rate.
When
Series
measuring
X.
maximum
Yeah,
luminance, half of the squares
that
on this
would
checkerboard
be great
are
too.
at 10,000
Hopefully,
nits,
once
the
Gaijin adds
maximum
mesh
value
shading and sampler
the
feedback
other
and
squares,
performance
the
improves.
user adjusts the brightness to be brighter or darker until they are
Should add
visually
DirectML too
indistinguishable
because they
from the
have
max
DLSS
signal
on
squares.
PC.
And for minimum luminance, the user's instead comparing to 0 nits or fully black. Best practice is to give the user clear instructions that don't get bogged down in technical details and show them examples for what both success and failure look like. And finally, best. We have two pieces of guidance here. First, you might have noticed that the previous basic calibration steps only affect the extreme highlights and shadows in your game. But users are going to want to control how the midtones appear, really the vast majority of your game's content. In the next slides, we'll cover 3 additional color controls that you should implement. Now, the other best practice is to not just show a test pattern, but to let users preview their adjustments on either a pre-rendered screenshot or a live in-engine game scene. For example, what if you have a stealth game where the character is sneaking around in very dark environments? In this case, when your user performs display calibration, your game might respond very differently than a generic test pattern such as the ones I showed previously. Let's dive into the additional color controls. The first one is paper white brightness. This is a concept that's somewhat unique to HDR games. Paper white literally means how bright a piece of paper or other diffuse white content appears in your game. It's implemented as a multiplier in linear gamma. Paper white is really important to implement because a user's preference will change depending on how bright their room is at the time they're playing. And if you're familiar with the Windows 10 settings app, it has an HDR brightness balance setting. This is doing exactly the same kind of gain adjustment.
Yeah, that right. They should do
for
that.
Windows
yeah,
SDR apps.
Like I said, if they have to, put it under some kind of idiot-proof thing,
and this behaves mostly the same.
Please
as
do
in
it.
SDR games.
I will gladly
you can tune
take that
contrast to preserve more details,
more graphic
in shadows,
freedom
or highlights in a scene. And this is implemented with a power or gamma function. The final adjustment is saturation, which is also a familiar concept from SDR games. This adjusts how rich or vivid your colors appear. It's implemented with a color matrix.
Sorry. Goof, goof.
The second part is showing an in-game preview of your HDR calibration and adjustments. We're going to use Gears 5 as our example, which does an excellent job of providing a ton of control and information to the user, but still keeping things very clear and actionable. Gears actually shows 4 different preview scenes. 3 are screenshots and 1 is a live in-engine scene. And these reflect the variety of environments and content in the game. As in the system calibration example, it gives very clear and prescriptive guidance for what users should do and look for. Now, wherever possible,
I think my ears just died. Oh, I'm sorry. Like I said, my mic is
easier for users
really
to replicate
a kind
those
of piece of
adjustments in other
shit.
systems.
So
and if those
it
adjustments
probably
are
was
measured
all
in
blown out
real-world
when I
units,
coughed
such as
there.
nits, use those units because this can be more intuitive for experienced users. All right, now on to our final topic for the session, auto HDR. Everything I've talked about up until now has about building native HDR implementations into your game. Auto HDR, on the other hand, takes an existing unmodified SDR game
it's interesting
and
to me
enhances
that
its colors to use both HDR brightness and HDR color gamut.
Minecraft on Xbox
gamers,
consoles, like Bedrock Edition,
free visual upgrade.
does not
I've already
support
purchased my game,
auto
and suddenly
HDR,
it looks
but
more
Minecraft
rich and more vivid
Dungeons
on my HDR
does.
display.
Like, you would think
with
the similar art style and stuff, like it would work perfectly fine, but apparently not.
Of course, while auto HDR provides an impressive visual experience, it's not a replacement for building your own HDR implementation.
Well,
you're always going to get the
some devs are certainly going to use it as one.
By doing it yourself and following our guidance. Okay, I'm excited because we finally got into the demo. I want to show you just what auto HDR looks like. Now, unfortunately, it's impossible to accurately represent the benefits of HDR when showing an SDR video stream. So I'm going to do the next best thing with a visualization of all the colors that auto HDR gives you that SDR can't reproduce. This is an in-engine cutscene from the opening of Gears 5's Hivebusters expansion, which came out just at the end of last year. On the left side of the video is the original SDR, and on the right side is the heat map visualization of auto HDR. Everywhere you can see colors on the right side.
Bedrock Edition has been forgotten on next gen. Yeah, I think they might. Hopefully, it's just they're working on the ray tracing right now, and that's why it seems to be forgotten. But yeah, it's a bummer. I feel like they're holding off as a test bed to show features whenever. Yeah, like I said, the ray tracing, DirectML, etc.
HDR game data. Just like good quality native HDR, auto HDR isn't simply about making everything brighter. You'll notice that it doesn't affect the appearance of most of the objects, such as people or things with diffuse surfaces. Instead, Auto HDR focuses on enhancing the highlights and shadows in the scene, most visibly the explosions and flashes as flashes of light as this plane flies through the storm.
I mean, Java Edition's honestly off in a worse state that when it comes to HDR than
but hopefully it lets you visualize what kinds of enhancements Auto HDR
Bedrock
provides
is like,
and where it makes the most
difference. If you have HDR enabled in Windows and you go full screen in Java, it disables HDR system wide
in its original colors. You can find it at this YouTube link.
And it looks really bad if you play it just in windowed mode with HDR on.
Otherwise, both sides are going to look very similar.
Whereas Bedrock on PC, it might not. I don't think it has native HDR support.
Now, if
but it doesn't look terrible, and it doesn't turn HDR off system-wide when you go full screen.
HDR. Why does it need Auto HDR?
That's always good.
And you're absolutely right. Gears 5 has an excellent native HDR implementation, and so no real user is actually going to be running it with Auto HDR. Instead, the reason why I've used Gears for my demo is so that we can directly compare Auto HDR versus high-quality native HDR. Here, I've taken a single frame of the previous.
Yeah, again, like I said, they suggest that they don't want devs to use Auto HDR as a replacement for native HDR, but you know there are going to be some devs who are going to do that.
HDR rendering a higher peak luminance with the volcano's flames, and it preserves more details in bright areas like these clouds. Here's the second frame, and we can see that the metallic surface of the helmet once again has more detail with native HDR, and then the glowing patches on their flight suit are significantly brighter. Okay, back to normal color images. So as you may know, Auto HDR first shipped with our latest generation consoles, Series S and Series X. Xbox has a long-standing tradition of enhancing the visuals and gameplay of your existing titles. Depending on the game, you can get unlocked frame rates,
and
widescreen support,
let us
HD
choose.
and 4K
let us power users choose when to use Auto HDR and FPS boost.
Auto HDR is enabled by default for all background.
Stop being so controlling about who can use it or what games can use it
from the feature. And we've been really, really happy with the consumer response to Auto HDR on Xbox so far. The obvious question was, can I get this on Windows? Here on the DirectX team, our goal is to take cutting-edge technologies such as DirectX 12 Ultimate and Direct Storage and provide a unified platform across PC and Xbox so that all of our gamers can benefit. So it was really exciting when we announced earlier this year that Auto HDR is coming to Windows. You can find all of the details on our blog.
Well, I'm ready for that too, whenever it comes to the non-insider builds.
This encompasses the vast majority of gaming hours spent on Windows. And the best news is that you can try it out today by signing up for the Windows Insider program and joining the dev channel. You'll need the same basic system requirements.
I want Modern Warfare 2 FPS boost. Just let me do it. Yeah, I know.
GPU and driver. And you'll need to turn HDR on first.
That is very frustrating. Like it's on PC. I mean I get it. Like if you want total freedom, you go PC, but that doesn't mean I'm going to not push for the similar things on console. But it's like on PC you don't get devs don't get to say, hey, you can't turn off VSync off in your NVIDIA control panel. That's ruining my developer vision. Like what?
We use
for information. Why is that a thing on console? Come on.
To determine if your game is eligible for Auto HDR. Running as a shader does mean that there is a small but measurable performance impact on both your GPU render time and the allocation that's needed for an additional HDR swap buffer. The render time overhead is mostly independent of your game's workload and instead scales with your resolution. On Windows, our philosophy is to always give gamers control over how their system behaves. Therefore, in addition to the operating system's eligibility checks, gamers can turn off Auto HDR on any app by accessing the advanced graphics settings. And just as a reminder, an optimized native HDR game can integrate the HDR display mapping into its final output shader and avoid the overhead that Auto HDR incurs. We consider the underlying Auto HDR decompressor. We trained Auto HDR on billions of pixels of HDR game output. This allows us to recover the color data that has been compressed by modern games' internal tone mappers. Depending on your display's capabilities, Auto HDR can expand your game's SDR colors to target up to 1,000 nits and the DCI-P3 color gamut. I talked earlier about how we tuned Auto HDR to minimize the impact on your game's color grading and artistic intent.
Oh, shoot,
We've done extensive testing, and we think the vast majority of games will look better. For example, natural or photorealistic lighting styles work really well with the algorithm. On the other hand, some non-photorealistic styles may have unexpected results. For example, if your game has a visual style that resembles a graphic novel and it has a lot of elements rendered at full light. And of course, you always retain full
nice
control
machine learned
over building
trained method
HDR
on billions of pixels of game data.
And with that, we're at the end. So
clearly Microsoft could do something along the lines of DLSS,
HDR
with DirectML Super Res.
They
just haven't done it yet.
And there's never been a better
because they pulled off
to build
something similar
with to target the rapidly growing PC market.
With
Second,
Auto HDR.
Microsoft is working with the ecosystem to bring you higher quality and more consistent HDR displays.
Series X like PC experience is expensive.
We've shown you techniques for how to get
PC
the
experience
maximum
in general is expensive right now because of GPU shortage.
And finally,
I'm
Auto HDR
really glad that I got my PC when I did.
SDR games. But of course, ultimate control comes from building HDR support yourself. For your viewing pleasure, here are all of the external links and videos that I've referred to in this session. And you can also find these links in the session resources. And as one final note, I want to give a personal thank you to everyone who's a part of this incredible gaming industry and community. This last year has been so challenging in so many different ways. But for me and many of my friends and colleagues, video games have been a rare beacon of hope. They've entertained us, they've comforted us, and most importantly, they've connected us with our loved ones, no matter where in the world we happen to be. So from the bottom of my heart, thank you for being so awesome, and may we meet each other again on the other side.
All right. So that's that. All right. So I know some of you guys wanted me to go back and watch and re-show, what was it? Let me find it. The hardware innovations. And hold on. Because we have a break from now until about 3 p.m., I'm going to go do that. So hold on. Actually, I haven't actually watched this. Now that I think about it, I just looked over the PDF real quickly to see if there's anything new.
Welcome everyone, and thank you for joining us today for our talk on the hardware innovations that went into the design of the Xbox Series X. My name is David Sutherland, and I'm a hardware engineer here on the Xbox team at Microsoft. And I'm joined here today by my colleagues and fellow hardware engineers, Andrew Odell and Marco Maswa. I'd like to start off by acknowledging all the truly amazing work that went into the design of this console. It really was a team effort from hardware to software to services to content. Each of these subject areas could have been their own presentation easily. So we're really only scratching the surface here today, but hopefully this is an interesting deep dive into what went into creating this console. So today we're going to start off by introducing the product pillars that drove the definition of the Xbox Series X hardware. Then we'll discuss my personal favorite topic, the speeds and feeds that were required for our hardware to meet these aggressive performance goals. And then we'll be diving a bit deeper into some of the trade-offs that resulted from these aggressive performance targets, including the innovative tower form factor, the thermal architecture, and many other system-level innovations. So to kick things off, at the outset of the Series X program, we knew that we wanted to build the most powerful Xbox ever, and that we wanted to focus on enabling developers to deliver the most incredible gaming experiences possible. To achieve that goal, we really established 3 primary pillars for the design of the Xbox Series X. We really wanted to create that most powerful next-gen console with 12 teraflops of GPU power, and that doubles our GPU power from the Xbox One X. And then we wanted to make sure to improve physics, visual fidelity. We want to give the most immersive visual experience possible. 4K, 120 FPS. We wanted to just cut load times to the minimum. And then we wanted to make sure that you had the best version of your games, that you had a huge back compat library with 4 generations of Xbox content, and that you were able to, harness that power of the Xbox Game Pass and that huge game library to play all your games. And, to kick off that, I'm going to hand it off to Mark, who's going to talk about the engine that powers the Xbox Series X, our system on chip.
Thank you, David. At the heart of the Series X is the system on chip. This was designed in partnership with AMD and manufactured at TSMC on its 7nm process. What's most interesting here is the significant increase in transistor count and almost an over 2x increase in the number of transistors as compared to the Xbox One X. As we go through this presentation, I'd like you to keep that in mind, as this will have a significant impact on the design of the Series X. To the left is a die shot of the Series X SoC. I'd like you to keep in mind the location of the different IP blocks, as this too will have a significant impact in the overall design of the system. The memory subsystem on the Series X was designed to run GDDR6 at 14 gigabits per second per pin bandwidth and has a total capacity of 16 gigabytes. An interesting choice was made here, such that 10 gigabytes of memory were dedicated towards game titles and 6 gigabytes were dedicated towards the operating system. The 10 gigabytes of memory has access to the full memory bandwidth of 560 gigabytes per second, whereas the operating system has access to 336 gigabytes per second. Running GDDR6 at 14 gigabits per second as compared to the 6.8 gigabits per second on the Xbox One S made us think about quite a number of things. We had to think about new PCB materials, a new PCB stack-up to ensure that we had good signal integrity on the memory bus. An interesting challenge too was power of the memory devices. Our initial extrapolations of what we expected from the GDDR6 parts as compared to the GDDR5 parts was completely different from what we saw when we built out the system and started running some tests. Another aspect of the system design was the EMI. EMI, or radiated emissions from the GDDR6, was much more than we had expected during early development. Finally, this whole concept of running 10 gigabytes of kind of dedicated towards game titles and 6 gigabytes dedicated towards the operating system meant that we had to use 2 gigabyte devices and 1 gigabyte devices. That means, or meant, that we needed to optimize for both signaling and timing in terms of latency for the different devices. The Series X introduces a generational leap in performance.
6 gigabytes for no, it's not 6 gigs for the OS. It's unless I just missed something stupid there, but it's 6 gigabytes for non-GPU stuff. 2.5 gigs for the OS, 3.5 for games for non-GPU stuff, and then 10 for games. That's all for GPU stuff.
Number of CUs or compute units, but there's also a significant increase.
I mean, I wish that they had just
on the CPU
bitten the
side,
bullet with the cost and gone with 20 gigs, but what are you going to do?
And also a significant uplift in frequency. For the memory bandwidth, as we move from GDDR5
because it's weird because the Series X dev kits have 40 gigs in a 10 chips and a 320-bit bus, so each chip is 4 gigabytes. But then the Series X has only 16 with the split memory thing. It almost feels like it should have been 20 gigabytes. I just have no idea why they went with it.
Interesting challenge.
Frustrating, but
design. I'll now hand it over to David, who will dive deeper into that.
Thanks, Mark. So as Mark alluded to, we're all bound by the laws of physics, and none of this performance comes for free. So when you make things go faster and you keep all of it in the same area, your power density goes up. And that's really a challenge for system design. So when we look at things like this 3 to 4x CPU performance generational leap and the 7-nanometer process,
who knows what they're going to do with future consoles? I personally still believe in the whole like 2 to 3 year kind of mobile phone like cycle.
The console.
I think Microsoft, possibly even Nintendo, will adopt that.
We have to think about how to size that power supply. We got to make sure that it has full capacity for your worst case load, so that when
I don't know
you play a game
once
and it does something
I really
that's high
suspect
power,
once the new Agility DX12 and
we also need to think about
GPU compilers and
ensure that every rail meets its peak power requirements.
And of course, sampler feedback start getting used. The 16 is going, the split memory is going to hurt less, but
so that impacts not just what you think about the heatsink design, how we put the box together, but the form factor.
I think
what's the fan?
Yeah, like I said, I still would prefer the 20.
We'll go into a little bit more about these kinds of trade-offs. So I'll hand it off to Andrew, and he's going to talk more about how we arrived at the form factor.
Thanks, David. So if a picture is worth 1,000 words, then this picture we're looking at sort of tells the story of the early Xbox Series X development and design. What we're looking at here is some actual
20 gigabytes would have made more sense, but
and you can see there's various form
maybe
factors.
It was like
ratios,
what they said is
sizes,
that the 16 was chosen for cost. What
I
was saying is I wish they had just bitten the bullet on that last 4 gigabytes
in the past.
But
and one of them is a little bit different, and it's the one front and center
again,
there.
Once we get SFS and GDK and the compilers fixed, it's not going to be a problem. But
for a long time, since before the Xbox 360 launch.
As it stands right now,
the 20 would have different form factors, the really ones don't win out for various reasons. We make trade-offs with mechanical engineering and electrical engineering. We'll go into some of those, but in this particular case, the different console did win out. And the primary reason for that is acoustic performance and thermal performance. The tower form factor just really provided better cooling for the cooling challenges we faced with these high-powered internal components, as well as providing better acoustic performance or a quieter console and a better user experience. So when we think about the tower form factor, we think about how we design the console. The early design, like I said, is an evolutionary iterative process.
Oh, by the way, if you're still interested in more about this, definitely go watch the Gamers Nexus console slur and photography videos and thermal testing, because they have some real in-depth
and especially user experience.
They have some real in-depth investigations as to
we might propose
how
we grow the console by 2 inches wider and taller. That really helps solve this thermal solution or this voltage regulator solution. And ID might say no, that
Microsoft might not cover.
But they might come to us and say, "Can you make it 2 inches thinner, or like a laptop?"
And it's just kind of neat.
And we'll say, "No, that's way too expensive. We can't do that." Or they might do something. Sometimes they come along and say something like, "Can you make it like a sphere, like a Death Star?"
A sphere.
Say, no, we can't do that.
The game sphere.
But we started this process on this console back in 2017, early 2018. So right after the Xbox One X shipped, and 2 years before we even had silicon for this console. And what we found when we started looking at it was that the thermal simulations and models we created showed that the tower would actually be significantly smaller than an equivalent console design. You can see that chart on the right kind of shows what our initial tower concept, how big it was, what the final was, and what our console concepts ended up being when we looked at the thermals were actually quite a bit larger. These other form factors may not have fit so well inside some entertainment centers. They might have had other challenges. They would have been, and by and large, we think they would have been louder than what we ended up with. So we really made this trade-off early on to manage the acoustics and thermals. I myself was taken aback when we really headed down this path for real. I was taken aback by this tower concept, saying, this doesn't look like anything we've ever shipped. Are we making a mistake? And I think a lot of the world was taken aback initially, judging by the reaction when we revealed it at the Game Awards, and like the internet was full of hilarious memes 30 seconds later with our tower console concept. But this tower console really offered some challenges and some opportunities, and we'll talk about those here in the next slide. So one of the big challenges was by going to the tower form factor, we had to split the motherboard into two. And this is new for Xbox. We've always had an atomic motherboard, one big motherboard where all of the firmware and hardware and software lives on one board. Its design is one unit, tested as one unit, manufactured as one unit. This case, we're splitting it in half, and we split it into the SOC board, or system on chip board, and the Southbridge board. The SOC board, is we've already talked about, is the heart of the system. It's where the SOC
I can't
and
think
the
of any
memory and the
consoles that
high-speed
had
video out and all of the power delivery, the power that beast live, as well as the internal and external SSDs. So if you think this thing looks kind of like a big video card, that's for a reason. It really is a big video card.
Unless you want to count
with
like
some storage on
add-ons like the Famicom
and if you look at that picture on the right, you see that, if you look at the SOC and the memory inside that fence and the voltage regulators right around it, that whole compact unit really sets the size of the box.
Series X should have been a Death Star-looking console.
That's about
the
Southbridge board is basically a redesign of our existing I/O boards with USB, Ethernet, radio, etc. But one of the opportunities here was by concentrating all the high power and high frequency components on one board, we could target the thermal solution and the electrical solution at that one board, meaning we use more advanced PCB material to handle the higher speed signals just on that board as opposed to the entire system, a larger motherboard. It also meant that we, to deliver all that power, we had to use extra copper density.
That could very easily roll around on the floor. Well, they'd probably do something like,
just the board that needs it, not the whole system.
Shave off the bottom so it
the
can
resulting solution, though,
flat,
how we connect the boards together was
the stand like the PS5 does.
Essentially, we had to figure out how these two boards are going to communicate, what's the most efficient and reliable way to do it, and we settled on an 80-pin board.
Come on, do you really think they're just going to put a completely spherical console there and not consider that it would roll around?
And the electrical team trying different types of connectors, different cable solutions, multiple cables, coax cables, a riser card, rigid solutions, and really this is the one that fell out to be the most manufacturable and the most reliable and met our needs. One other thing to consider here is how a console gets designed. So the design process for the console, as I mentioned, starts years before we ship and even years before we have working silicon. So we have to do a lot of the design up front using assumptions and working with assumed risks. So we iterated on this design for 2 years before we ever saw the first silicon. That involved doing things like building thermal load boards, thermal systems that look like this, that perform in a similar thermal manner so that we can validate our models and see if we're actually building the thing we think we're building, as well as high-speed test boards and voltage regulator test boards and different technologies to help us mitigate some of these risks. And then one thing I would add the split board design allowed us to do is to target our EMI, or interference, or electromagnetic interference mitigation to one board with those shields around the memory and targeted shields around high-speed circuitry, as well as targeted filter solutions at the interfaces to the other board and to the outside world. And our compliance and radio teams really helped drive that solution for us early on, so we didn't run into any troubles there. And with that, I'll hand it back to David to talk a bit about the thermal architecture.
Hey, thanks, Andrew. Yeah, so as we talked about, we built a beast of a machine, and it has a lot of power. And by splitting the board, we created an interesting new challenge for the Xbox team and how we're going to tackle this. So we kind of had to rethink the way we approached the thermal architecture of the Series X versus what we had done with the One X or the previous consoles. So traditionally, you have the cool air flow in from the sides or the front, and then blow out the back. But in this particular case, we basically had all the cool air come in from the bottom of the console or the back of the console, and then it's pulled through the console by the fan and blown out the top. And to break things down a little bit more from there, the way we can think about this is that basically the system is built around a center core. We call it the center chassis. And that can be thought of as kind of like the backbone or the spine of the system, both mechanically and thermally. And we do use it as a heatsink for some lower power components like the Southbridge PCB and some of the things on the backside of the SOC board. But really, where the thermal architecture really shines is with the vapor chamber and with the heatsink. And you can see that all of the hot components are on that side of the board, on the heatsink side of the board. So that's the SOC, of course. It's the DRAM and the voltage regulators that power the SOC. All of those touch off on the vapor chamber. And that allows us to sink that heat very effectively into that heatsink, and then the fan pulls the cool air through and is able to dissipate the heat. Also note that on the other side of the board, kind of the cooler side of the system, we have the more sensitive components, the optical disk drive and the PSU, and those components get cooled by kind of a parallel path of airflow. One other thing we really spent a lot of time optimizing on was the fan itself. So the thermal mechanical team spent months and months optimizing the fan design with our partners. Different shapes, different number of impellers, all kinds of different designs to get us at the maximum airflow for the minimum amount of noise. And another thing that the mechanical team worked on was something that kind of goes overlooked. It's called the X spring. It's how we mechanically attach the heatsink to the board, because you need to have compressive force there. And we had used the same X spring design for a number of generations, and changing that as a result of having to have capacitors on the back of the board, we couldn't use the existing design, so we had to completely redesign that. And it's a bit of risk, because that component is has a lot of impact on the thermal performance of the subsystem. But by redesigning it, we're able to get optimal TIM pressure, so the compressive force there, and we're able to put the capacitors where we needed them for power delivery. And one other thing we wanted to highlight was before we got hardware, we spent a lot of time in modeling, and this was doing thermal simulations, doing airflow simulations to try to arrive at a really good design point, so that we had to do minimal mechanical iterations. So the team did an amazing job there. If you've had one of these in your house, or you've played with one of them, you know how much time we spent optimizing the acoustics and the airflow on this. These things are really, really quiet, and we're super proud of how quiet the experience has really been. A big part of that is due to this vapor chamber. And for those that aren't necessarily mechanical engineers, a vapor chamber is basically a hollow chamber with a vacuum, or under vacuum. And inside of that chamber is some water. And what happens is when that one side of that vapor chamber gets hot, the water inside of the chamber vaporizes and flows throughout the chamber, and that heat energy from that water vapor is transferred onto the other plate and eventually into the heatsink. And it does a very efficient job at doing this, and it allows us to achieve a really minimum acoustic profile while keeping our heatsink size down, because we could make a giant hunk of aluminum, but then your console would be super heavy and it would be clunky, and we wouldn't want that. So that's why we arrived at the vapor chamber solution. So on the other side of the coin here is, obviously, in order to have something cool, you need to have power, right? It's kind of thinking of it backward. We wanted to really optimize our power profile for this console, because ultimately we don't want to have to cool the power. So it'd be great if we just didn't create it in the first place. Now that doesn't work as well for gameplay modes where you're trying to put as much performance as possible into the box, but for scenarios that don't really require the performance, we don't want to be running at max frequencies, because it's just wasted power. So we spent a lot of time with the software team, with the firmware teams, the content folks, to make sure that we were running at the optimal frequency for power consumption. So these are for modes like media playback, and for our standby modes, instant on and energy saving mode. And you can kind of see here, we broke it down by percentage of SoC power versus gameplay. So for media streaming, let's say you're loading up your favorite media app, and today it's running at about 14% of the SoC power of our worst case gameplay power. And this is really a testament to the optimization we did. This would have been 25% higher had we not done the optimization. And same thing for our standby modes for background download.
I almost get the feeling like Microsoft knew exactly what kind of hardware Sony is going to have. Like, just
meticulously optimized to save power.
I mean, obviously I have no proof, but it's just, that gut feeling. Trust me, bro.
Obviously, we want to save you on your power bill. We don't want to burn the power. We don't have to cool it.
Sure.
But also from a sustainability standpoint, we don't want to have to emit the carbon of that energy that was consumed by the console. So by reducing the power in these surprisingly high usage modes, a lot of people watch videos on their Xbox, believe it or not, it's not just for gaming. We wanted to keep the power to a minimum so we can have a minimal carbon footprint. And with that, I'm going to toss it back to Andrew, and he's going to tell us about our power delivery network.
Thanks, David. So that Xbox SoC that we've been talking about, Xbox Series X SoC, is the highest performing and the highest power one that we've ever had to deliver. And the key to that is the voltage regulator subsystem that delivers actual power to the SOC. In order to do that, we needed to squeeze more power into a smaller space. And so this graph on the right shows just kind of a rough representation of the amount of power being delivered in watts per square inch of board area, or per millimeter squared. And you can see that starting with the Xbox One X, that curve has a knee in it. We really started getting more dense, and that trend only intensified in the Xbox Series X generation. The key to that is that starting with the Xbox One X, we went to the digital controller. So we use dual and triple loop digital voltage regulator controllers from MPS, meaning they control multiple rails at one time. And that's not unusual. We're certainly not the only ones doing that. It's very standard in the industry these days. What is a little more unusual is that we really rely on the high accuracy telemetry that these provide. And we've worked with MPS to tune that down to where we're accurate both at high power and at very low power consumption, so that we can really make these measurements accurately in real time. So what that means is that for characterization and debug of the silicon, for looking at different titles, for manufacturing, for field performance, we can look across, out in the field how the consoles are actually being used, how much power are they consuming in which titles, and what does that profile look like. We're able to gather all that information and really optimize the power consumption, as David was mentioning. And as he mentioned, the key to that really for reducing our overall power usage is the lower power states where the consoles actually spend a lot of their time. This allows us to do that. And you can see at the picture below, kind of showing what an Xbox One S voltage regulator looks like compared to an Xbox Series X voltage regulator phase, one phase of the regulator. And it's about half the size, but it's delivering quite a bit more power per phase. So the actual power density is much, much higher. The second part of the design there, or I should actually mention, one of the other things this allows us to do at manufacturing is to adjust each rail of each console, of each SOC, so all the different voltages independently for that particular SOC, so that we can optimize the power on a per console, per rail basis and across different power states and really deliver the lowest power console possible, still meeting the performance guides. Another thing that we do in this design phase, and David talked about this with the X-clamp, is we redesign the power distribution network underneath the SOC. We optimize the capacitor placement and selection to reduce the voltage droop in these high power scenarios. And that really comes into play in some of the early silicon development, because as we mentioned, we're designing this box months and years before the silicon is actually available. And that means that we really have to have it ready to go the day the silicon arrives so that the development on games can start.
I just saw
iPad
that
Pro
really is getting the new M1 processor.
And with that, I'll hand it back over to Mark to
this
talk
thing
about
that's going to completely
solution.
trash the SQ2 surfaces. What's the news, Kirby?
Well,
what do you mean? What do you mean? What's the news? Anything specifically you're thinking of?
Transition from a hard disk drive in the One X to a solid state drive. This allowed for a significant, in fact, an order of magnitude increase in the raw
I had this too small.
Of the storage subsystem. In terms of system design, this meant routing PCIe Gen 4 to a solid state drive in an M.2 form factor. Another area of significant innovation was in the storage expansion card. This was designed in partnership with Seagate. What it allowed for was for a plug-and-play user-expandable storage solution without an impact in game performance. There was tremendous work in system design, also allowing running PCIe essentially to a connector and to the storage card. And there's a significant amount of work in both electrical and mechanical and thermal design to make this all work. Really great work from the storage team here. All these innovations were the platform for things like Quick Resume and the Xbox Velocity architecture. I will now hand it over to Andrew to conclude the presentation.
Xbox
Thanks,
buying
Mark.
PlayStation. What's the most exciting thing shown
so
today?
we're running a little short on time, but we just wanted to
probably
kind of say thank you and
the
to talk
new
about
sampler feedback demo,
what
in
something
my
we're so proud of
opinion.
this console. the Xbox Series X is the most powerful console we've ever made.
There's
a huge number of innovations that
totally
went into
new
it,
to
not only
me.
from the hardware teams, from mechanical and electrical
and they showed that, you know, you can get even more performance than they originally promised in certain situations,
all
which
the content
is,
delivered.
of course, fantastic.
But I mean, the key takeaway
so
from us
I
is
guess
this is something
the
we're
most
really
exciting
excited
thing
about. We
was
love building
the new
consoles, we
SFS
love
stuff
playing games,
and Velocity.
It's something we're very excited about, and we spent years of our lives working on this, and now it's kind of up to the developers to go harness this power and really light up experiences for our Xbox gamers. And the hardware team is really excited to see what you come up with. So thanks for listening.
All right, that was that. So hold on. Our next presentation, denoising ray trace soft shadows on an Xbox Series X and S and Windows with Fidelity Effects, presented by AMD. That is at 3 p.m. So it's a little less than half an hour. So I mean, I'm going to keep the stream up, but I am gonna, if I don't reply immediately to you, if you put something in chat, just know that I'm like kind of doing something else in the meanwhile. I am really excited to see how first-party devs use the features in the new Xbox. It's going to be fun. Yep, definitely. Also, I really want to know, like, what the deal is with Phil having a Switch on his back shelf, and then Sarah Bond in the intro keynote also had a Switch on her back shelf. And, you know, there was no PS5 on the back shelf. It'd be different if they just, you know, if she had all the consoles, because it's like, oh, gaming, kumbaya, whatever. But I can't help but think after they hid in plain sight the Series S, the Indiana Jones thing, and then the Xbox headset, that that the Switch means something. Xbox buying Nintendo confirmed. Yeah, no. You think DX12 Agile is a big deal with devs not having to wait for? Yes, that is that would be probably my most second, you know, big thing. Obviously, Agility DX12 is going to be a huge win. 100% something going on with Nintendo Master Chief Smash. Well, we'll have to see, but I'm putting on my tinfoil hat and thinking it definitely is something. xCloud Game Pass, xCloud version for the Switch, or Game Pass. I know this sounds crazy and probably would never happen, but Nintendo games on Xbox. Yeah, I mean, Game Pass, I think, is a definite possibility, in particular xCloud. And about there's an ice cream truck in the background. I don't know if you can hear that, but Nintendo and Xbox publishing their games on each other's platforms. I'd be all for that. Of course, I've said many times, in a ideal world, we wouldn't have any exclusive, like, games would release on every platform where they are technologically and financially reasonable to do so. So, and platforms would merely compete on delivering the best experience as a platform, because that's what you're buying, or compete on selling the games at a lower cost or whatever. But I think the Nintendo games on Xbox and Xbox games on Nintendo might be a little bit of a stretch. I mean, obviously it's possible, who knows, but yeah, it makes the most sense for at least Xbox and Nintendo, because they're both different and eat into each other. Yeah, I mean, you're right. You're right about that, but I mean, you do have to convince Nintendo's executives and their top brass, old conservative Japanese businessmen, that is the case, and good luck with that. I doubt Nintendo fans would stop buying Nintendo console and buy an Xbox instead. Right. I mean, like I said, I own an Xbox Series X, a Switch, and a gaming PC. It's the people who the money lost would probably be a lot less than what they gain. But again, you'd have to convince Nintendo's top execs of that. And I mean, good luck. We can't even get them to give us a decent online service, and they keep acting like spitting out retro games turned battle royale and NES and SNES games somehow justifies paid online that's worse than the 360 era. I mean, like, it's totally possible, but you'd have the monumental task of convincing Nintendo's heads that that's the right thing to do. Nintendo's motion control stuff, that's already a reason known as Switch, the experience. I mean, for me, it's less about the motion controls and more about the software, two, the convenience, and how the device itself is cool, hybrid. It's most likely just xCloud. Yeah, I think that's the most likely thing. Because we've had rumors, I think since 2018, that they're working on it, and I have modded my Switch with Android to try out xCloud on it, and it doesn't it would be the premium experience, in my opinion. Like, I would rather do that than play on a phone, because I get a much bigger screen and high quality controls, bar Joy-Con drift, without something that's too big to keep in your pocket, like a iPad or Android tablet or something. It kind of, I guess the Switch kind of strikes that perfect middle ground between a phone and like a tablet. Plus it's got the game, it's centered on gaming already, so yeah. Controls is the biggest issue with xCloud IMO. Well, at least it's not trying a PlayStation controller, because the only difference between Xbox and Nintendo is A, B, and X, Y are swapped in positions. Apple, the iPad Pro has console-like graphics. Proceeds to show PS 2.5 mobile games, despite the hardware being capable of more. I mean, it's like, it's probably developers didn't go to, how do I put this? Like, I guess when you consider like the landscape of mobile gaming and how it's dominated by a bunch of 2D gacha games, that those kind of graphics would impress a lot of mobile gamers. Let's just whip out this massive controller and this gaudy attachment for my phone, lol. Yeah, the Switch is, in my opinion, definitely the premium way to play xCloud. Oh. I'm just happy we finally have the requirements for direct storage on PC. That's all I wanted from this day. Well, that's good to hear. You know, I'm glad to hear that too. Of course, good thing is I don't have to upgrade my NVMe now. I can stick with my great budget, or not budget, but really value choice. So, you know, I'm glad about that too. Yep. All right. I think that overall, Gamestack 2021 has been pretty good. With direct storage on PC would give third-party devs a much bigger incentive. Yep, definitely. Yep, I gotta go. I will go now. Thank you for the stream. See you. Oh, see you later. It's, you know, good having you. You know, thanks for showing up. All right. Hold on. Give me a minute. I'm gonna mute my mic for a sec. All right. Sorry. Yep, it was great. Okay, I missed it. No, well, I mean, you can. If it's on YouTube, you should be able to scroll back and, you know, rewatch the stuff. I'm gonna keep. You know, hopefully YouTube will save this live stream. You only missed some of the talks. There's a talk in about 15 minutes on ray trace, on denoising ray trace soft shadows. On Xbox by AMD, and then right after that we have real-time ray tracing in Minecraft, presented by NVIDIA, and then that's it. Plus, I think, like, once the event is over, they will very likely go and upload all the sessions, because I mean, I missed some of them because I was doing this live stream and I didn't want to have two running at the same time, or having to mute one. But I'm pretty sure they will go and upload it to their YouTube channel, like all the after all of this. In fact, I will go check that right now. Nothing new right now, but I believe last year they had, you know, all the talks uploaded. So yeah, they should, after the event, they should come to the YouTube channel. I want to know how shader culling works with ray tracing. Shader culling for what specifically? Like geometry culling? Geometry. Well, here's the thing. Like, if you're doing a hybrid rasterization plus ray tracing approach, obviously having less geometry in your BVH is going to result in higher performance, because you know, there's less cycles are used to, you know, test against it. And obviously for the rasterization part, any geometry that's not visible, you know, there's no downside to culling it, so long as you're not, you know, as it is truly not visible. Mesh shaders, etc. But anyways, but with ray tracing, the problem is ray tracing simulates light, how it bounces around the environment. Like in the real world, if like that geometry or whatever, you know, it's still there whether we can see it or not, and light bounces are still affected by it. So if you cull your geometry and then build your BVH using the culled geometry, you may end up with physically incorrect. You will often end up actually with physically incorrect ray tracing. Even though the goal of ray tracing is to provide physically correct lighting. So it's a bit of a balance between how physically correct you want your ray tracing to be, and how, the performance. In terms of mesh shaders, well, again, mesh shaders are just kind of a replacement for the geometry pipeline. So the same principles apply. Like if your BVH is built using the full geometry without culling, then you're still going to get physically correct lighting. But if you don't, if you cheat or you use like whatever, you're going to get, you'll have the same issue whether your geometry is processed through a mesh shader or otherwise. That's what I thought. I'm interested to hear more. Thanks. Yeah. Yeah. Foundry here. Come on. Okay, good. So it looks like Resident Evil Village, when with ray tracing on, actually runs with a 60 FPS target, but the frame rate is uncapped. So that's a big win for variable refresh rate users. PS5 will be with energy CPR. Okay. Come on. All right, we'll go hop over to the new next show in a second here. Whoops. Effective, what is that? Hold on, I gotta do 13.5 times 2.5. Right, it's there. Okay, I gotta go to next one. Come on. All right, here we go.
Hello and welcome to my talk, Denoising Ray Trace Soft Shadows, here at Gamestack Live 2021. My name is Dominic Baumeister. I'm working as a developer technology engineer here at AMD, and I've been doing that for the last 4 years, or almost actually. As a developer technology engineer, my job is to work closely with game developers, like you probably are, to ensure that the new AAA titles that come out are well optimized for our hardware and fully utilizes the resources that it provides. End of last year, we released the RX 6000 series that is powered by the RDNA 2 architecture, which is the same architecture that also powers the Xbox Series X and Xbox Series S. And with that architecture, for the first time, we have support for hardware ray tracing, which in practice means we have support for hardware accelerated ray triangle intersection. And as part of that, we in our team figured it would be a good opportunity to provide you with a sample that really brings out the realism in your games. And that sample here is showcasing soft shadows and precisely the denoising part of that. So let's jump right into the agenda. So the entire talk will be split into 2 sections really. The first half I will go about the building blocks of that denoiser, and in the second half I will talk about some of the performance improvements that I made to make that thing really fast and shine on RDNA. But first, let's zoom out a bit and look at the 10,000 foot view. So a common technique to simulate area lights is to choose a random point on that light source and then try tracing a ray from that surface towards that light source. The general approach is to just increase the ray count until the final image converges and we have a proper soft shadow. If you do that with like only a few rays, you will see something like on the right hand side, and the right half of the drone is actually the noisy input that our denoiser receives, and then the left part of that drone footage is what the denoiser produces as a result. So yeah, usually you would average over multiple rays, but that becomes cost prohibitive pretty soon. So the job of the denoiser is to generate additional samples. And the idea here is that instead of shooting additional rays, we reuse the samples that we already have. This is both using neighboring pixels and the results that we got from there, as well as accumulating samples / rays over multiple frames. One important addition here, for a small number of lights, it's actually feasible to not denoise the entire RGB space, but instead denoising a mask, and this is precisely what we are doing here. The entire system is loosely based on a paper by NVIDIA called Spatial Temporal Variance Guided Filtering, which you can find on the link here. One additional disclaimer, I was only making that denoiser faster. The guy who initially wrote it was Guillaume. The denoiser itself is already integrated in a few titles. I'm only showcasing those here where I found screenshots I can actually use. So the first one is a pretty famous game called Dirt 5. That is pretty fun racing game. And the next one that you should check out is the Rift Breaker, which is an action-loaded real-time strategy game.
Oh yeah, this one was cool.
But there are actually more to come. So onto the first part of the entire presentation, the building blocks. The entire denoiser is kind of split into 5 conceptual passes. So we begin by actually creating that shadow mask that we want to denoise. Then we run some analysis on that shadow mask, which is called local neighborhood here. We do some disocclusion query. That is the third pass. and both the local neighborhood as well as the disocclusion and the shadow mask all feed into the reprojection step, which does the temporal accumulation. And after that, there are various filter kernels who will then do an additional spatial blur to remove the remaining noise. So on to the first of the building blocks, actually generating that shadow mask. As I said before, we are shooting rays towards the light source, and for that we actually count the number of rays that hit that light source. The idea here is that we are not utilizing any of the hit shaders because we can't really hit that light, but we can hit geometry. So what we actually do is, once we missed geometry, so in the miss shader, we increment that counter, meaning we miss geometry, meaning we hit the light source. So we increment the number of times the rays hit that light. And that counter value is then just stored out to memory, and that is then the shadow mask that we want to denoise. And we do some analysis on that shadow mask. In general, that means we are creating the mean and the variance over the local neighborhood, meaning a certain number of pixels around the pixel that we are interested in. That mean and variance is something that will come up a lot during that talk. So it's quite important to get some intuitive understanding for these values. The mean is really just the average, so usually it's some kind of shadow value, and the variance tells us how noisy the data is. So the more noise, the more aggressive the denoiser has to be usually. And using that mean and variance from the local neighborhood allows us to span some form of window in which we would expect additional rays to be in. So if we would have shot additional rays, we would expect them to generate values that are somewhere within that window. Think about what happens if an entire region would be in shadow. That means we have pretty much no variance in that. All of the values are in shadow. So if we would have shot more rays, we would kind of assume that these would be in shadow as well. And that is kind of that window that we have. If you look at the images here on the right, these show results from using different kernel sizes, so the number of pixels that we actually investigate. And as you see, the higher the region is that we look at, the better the results are usually. But of course, there is a performance trade-off. And here we settled with a 17 by 17 kernel. And one more interesting thing here, that filter can actually be split in a horizontal and a vertical pass, dropping down the number of samples that we require quite a lot. The next building block of the denoiser is creating a disocclusion mask. That disocclusion mask will tell us for each pixel in the screen if we can reuse the history data that is stored at that position. And we do that by calculating a reprojection value in two different ways, and then later trying to match the reprojection values. So the first way we do that reprojection
a huge fan of temporal techniques.
Project that surface position
I understand that they can
into
provide
and back into the screen space of the last frame.
I mean,
and that gives us a certain depth value.
I personally do not like the image quality loss.
The other approach
that can come along with
using
them at
per pixel motion vectors to look up the depth value from the previous frame's depth buffer, and that gives us the second depth value. And by comparing these two depth values, we can now check how close they are. And the closer they are, the more probable it is, the more likely it is that they actually belong to the same surface, and we can reuse the history information that we stored there. Using a constant depth threshold here is actually a bad idea. If you look at surfaces from very grazing angles, that means that you get these like streaking artifacts simply because usually for those, the depth buffer precision is not as good. We counteract that by increasing that threshold depending on the angle between the normal of that surface and the view vector. And that improves the situation quite a bit. And if you look on the image on the very right, that is how you would expect that the occlusion mask to typically look like. So on like the plane on the very bottom, there's pretty much no disocclusion. We can reuse all of the history values, but especially in that area where the rotor blades are, there's a lot of movement going on. A lot of the time, like, yeah, we simply can't reuse the history values. So that is what you get. And now both the local neighborhood and disocclusion somehow feed into the reprojection pass. So the very first step that pass does is it uses that disocclusion information that we just computed to determine if we should load the history moments or if we should reset these moments. And the moments that we track there are again just a mean and a variance. And so tracking our current shadow value, tracking how much noise, how much temporal noise there is, and it's also tracking the number of samples that we did in the that we have in that history. And that allows us to, for very like low temporal sample counts, to artificially boost that variance to make later passes more aggressive if our temporal, like our temporally accumulated values are simply not trustworthy enough. So if you look at the bottom of the page, these two images, on the left side without variance boost, we move the camera a bit, and so at the very bottom you see the noise region where simply not enough temporal samples have been accumulated to generate a noise-free image. And thus, if we now apply the variance boost, the spatial filters later will be more aggressive, and you see how that area is noise-free as well. On the very right, just one more thing to give you a good intuition for that is showing the temporal variance. And as you would expect, like in areas that are completely in light or completely in shadow, there is pretty much no variance. But in all of the penumbra regions, where it's sometimes in light, sometimes in shadow, where you have moving parts, that's where you expect the most noise, and indeed that is where the variance is the highest. The second part of the reprojection 20 minutes.
Anything big happen? No, not really. This is a really more fast-moving technical deep dive on AMD's Fidelity Effects shadow
if you would just
denoiser.
Naively blend our history values in there, you would see
we're about
like
we're just short of halfway through it.
Pretty much disappearing, and you wouldn't see the shadows there.
Check.
If we
we're just short of halfway through.
Reuse that window that we computed in the local neighborhood pass and clamp the history values towards that window.
Nothing major sense.
Remember, that is telling us which values you would expect. We get a much better shadows, especially in regions like these rotor blades. And lastly, we actually produce the shadow values as the result of the reprojection by looking up the past history values and blending the new sample from this frame into that. And here there is one more tricky bit. So if you have a very low blend factor, that means we heavily weight that new value that we just produces, but we are throwing away a lot of the information from the history. That means we get a very responsive filter, but it's not quite removing a lot of noise from the image. If we would do the other way around and use a very high blend factor, that would mean we very highly weight the history value. That gives us a pretty stable filter, but it's pretty unresponsive to changes. So since we already track the history samples, we adjust that blend factor based on the number of samples that we have available. Essentially meaning the more history we have, the higher we weight it. If we have less history, we weight it less as well. Now we have a pretty stable image, at least temporarily stable, but you still see a lot of spatial noise in there. So we use 3 consecutive filters. Each one is doing an edge-aware, a true wavelet filter. The first one with a 1 pixel stride, second with a 2 pixel stride, and the third one with a 4 pixel stride to remove the remaining noise. And one important part actually to make this work really well is to output the results of the first filter pass as the history for the next frame. And each of these passes additionally tracks the variance again. This is mostly to avoid over blurring in regions with low variance. So if we know that there's pretty much no variance, we don't run the blur, or at least weight neighboring pixels less. So if you look at the variance output for each of these passes, you see how the values for the variance decrease with every single pass. So we are removing the spatial noise from the image. One last important step for the entire denoiser is to run TAA on top, because in certain situations you can see some of these firefly artifacts that you see here on the image on the left. If you look at the chandelier, there are these like small white dots, and by adding TAA to the mix, that greatly improves the entire effect. Now to the second part of the presentation, performance improvements. There are 2 key observations to make this entire thing run fast. So the first one is we are very rarely actually shooting more than 1 ray per pixel, because although we have hardware that can accelerate the ray traversal quite a bit, we still like to keep that at a minimum and only shoot 1 ray per pixel. So we might as well move that assumption into the denoiser and see how we can improve it. The second key observation is that in a lot of scenes there are some like larger shadows or areas that are more in light, where actually the output of the denoiser is exactly the same as the input because there is no variance there. So we would like to skip these costly operations in the first place. So on the first assumption, single ray per pixel, what happens if we do that? So here on the right, you see how we calculate mean and variance for the local neighborhood. And if you now plug in for the value either 0 or 1, you see that both the mean and the variance become essentially the same value. So we can get rid of half of the computations and just track them as if they were 1. So that already helps us quite a bit. The second part is now we don't have to track like a floating point value between 0 and 1. We actually only track a single bit per pixel that tells us was the pixel in light or in shadow. So we can actually compress an entire 8x4 region of pixels into a single mask. A nice side effect of that, this nicely matches the native SIMD size. And if you're pretty familiar with, at least on RDNA, and if you're familiar with RDNA, we're actually tracking bools as a scalar unsigned integer anyway. So all we would have to do in theory is change our ray tracer to track a flag and then just output that scalar to memory. Either way, we compress the data quite a lot, and this will help us further, as I will show you in the following slides. And in theory, we can actually take that whole idea to higher array counts. That just makes a few of the later passes more expensive, or at least more complex to calculate. I don't want to go into too much detail on how we put that mask together. The key idea here is that on PC we use wave active bit OR on DXR 1.1. On DXR 1.0 the situation is a bit more complex because the thread group size is not defined for a region shader. So in that case we just write out the results 0 or 1 as we did before with the smallest target that we can find and run a separate compression pass, but that still helps a lot. As a quick example, I want to run you through the changes that I had to do for the local neighborhood. Remember, there was a split pass, so we're just doing the horizontal part of the local neighborhood here for that pixel lighting up here as a number 19. And since we did everything compressed, the left region is in 1 unsigned integer, the center region is in 1, and the right region is in 1 unsigned integer. The first advantage here, instead of doing a lot of vector loads, we just have to do 3 scalar loads to have all of the data available to do the local neighborhood for an entire 8x4 region, which is already quite bandwidth efficient. So that is now laying out all of these bits in like 1 row, and we go through the entire slide from the top to the bottom. So we start out with the left, center, and right as they would be presented in an unsigned integer, each of the single bits that we're interested in colored. And now we have to extract that 1 row that we are interested in, combine them as before. Notice how left and right actually switch. And then we shift out all of the bits that we are not interested in anymore. And that's the final bits that we actually iterate over. And if you think about that, we have a few scalar loads. We have everything compressed, and we do a lot of ALU to finally calculate the local neighborhood. So that is like quite important to achieve it that way. Now on to the next idea. We want to identify regions that we can actually skip the denoiser, and we want to do that in a cheap way. In practice, that was probably one of the best optimizations that I did. It obviously varies a lot from scene to scene, but overall that helped roughly in the 25 to 30% range. All of the denoisers run on 8x8 tiles. Then if you look at that 17x17 kernel, that means every like we have to do like an 8x8 boundary in each direction. So in total, we have to check a full 24x24 region for all of the values in there, if they are all in light or all in shadow. Remembering that we have everything compressed now in a single unsigned integer now spans an 8x4 region of pixels, we actually have to do only 18 scalar loads to address the entire region. And then we don't have to do any complex math. We actually just have to combine each of the masks, OR them together and AND them together, and then check the results of that AND and OR. So if the AND mask is all bit set, that means all of the inputs were in light. So we can skip the denoiser for that 8x8 tile. If all are in shadow, like if the entire OR mask is 0, that means all are in shadow, and we can skip the denoiser tile there. All in all, that means that that entire code is completely scalar. So we're not taxing the vector unit at all. That is only on the scalar unit, and helps us a lot for one of the next steps that I want to show you. But first, the tile classification pass generates what I call a metadata mask, and that is then used in the follow-up passes to do a quick scalar load, check which like logical paths we have to run on,
because
and either we clear or we apply the
that's
actual
something you kind of have to specifically add to an engine or game.
One important optimization here, we can actually merge a lot of these passes. Like the tile classification, the local neighborhood, the disocclusion, and the reprojection, they can all run in the same path. And by doing so, we can remove quite a lot of the intermediate resources.
Like new features and new graphics techniques are great, but a lot of times people forget
all of this made
someone has to write it. And
by compressing the bit mask.
It's not easy
making
always.
that local neighborhood computation that cheap. So we can get away with doing that a few times per tile.
See if they answer my question.
One more optimization for the filter passes.
At improving
These are the last ones
variable rate shading,
in
but
the,
certainly helpful in reducing the rate count for the initial tracing pass
each of
to
those
generate the mask.
has to access up to a 16 by 16 region. So we ensure that we load everything in blocks of 8 by 8. Keep that in registers until we have everything loaded, so we can ensure that all of the loads go together. Then we sync, center everything in group shared memory, and each of the threads uploads everything to group shared memory. Then we center in group shared memory, and then all of the samples then work off of the data that is in group shared memory. We want to ensure that we can actually keep the data as is and keep it as densely packed as possible in group shared memory. So we have to ensure that everything stays in a packed format. And we do that by annotating the resource view in the respective, like with that float 16 T2, and use that packing function here so the compiler knows how to interpret that data. And that's, in the end, the code that we get. So we have all of the loads in the beginning. Then we can do some packed math on all of the stuff that we loaded, and then just write everything to group shared memory. The last optimization that I want to quickly go on is it actually makes sense to keep, like if you're denoising multiple lights at once, it still makes sense to keep all of the resources separated. Especially if you do the final write out to an image and just write to a single channel of that texture, that would then result in a read, modify, write, and that is something we really want to avoid. For future ideas, like the one thing that immediately comes to mind, like
they mentioned VRS right here.
So that is like usually like a soft effect anyway. So we could maybe get away by tracing and denoising at half resolution and then do an effect specific upsample. More ideas, we can guide the ray tracing part. So it's always a good idea to trace few arrays. So we could just compare history frames. If we already are converged, then we might get away with shooting few arrays. Or we could reuse tile metadata or a VRS image. All of that is feasible if you can get away with fewer arrays. And that denoiser may as well be applied to ambient occlusion. That works as well, and Riftbreaker is actually doing that. All right, I want to thank everyone here on that slide for helping me out, providing me with ideas to improve all of that, and making it possible. Thanks also for Microsoft for the opportunity to talk here at Gamestack Live. The entire denoiser will be open source and will be available on our website, gpopen.com, next to our reflection denoiser. Thank you very much.
All right, so that was the second to last session. Finally, in about 10 minutes at 3:40 p.m. Eastern, we have Introduction to Real-Time Ray Tracing with Minecraft presented by NVIDIA. That's going to be about 30 minutes long. Almost done. Let me see. But I want AMD Minecraft ray tracing. Well, you're just gonna have to live with the Series X tech demo for now, I guess. Okay. Who seriously disliked the live stream? Hold on. Phone call. Sorry. So who seriously disliked the live stream? I don't know. Probably just some person who lets me live rent free in their head, or the guy I told that he should have signed up if he didn't like that I was doing commentary over it. That's the only thing I can imagine.
Here comes some more!
When does the NVIDIA RT thing start? It starts in 3 minutes, and then it's going to be about a 30-minute presentation, and that'll be the end of Gamestack Live, and I will, well, I'll probably stick around for maybe 10-15 minutes if people have any like other questions they want to ask me, and then I'll probably hop over to Twitch and start streaming some games, because I'm in the mood for that right now after over 4 hours of sitting here. All right, my agenda is good. All right, here we go with the last session. Marketing professors playing Marvel trailers during class because he's in love with the universe. I love this class.
To be one of the engineers working on Minecraft with RTX. This is going to be a short 30-minute introduction to real-time ray tracing. We'll touch on a few topics, and we'll go into some detail on how we produce an image using ray tracing, and how we can do nice things like per pixel global illumination. So what is ray tracing? You might have seen something like this explanation before, where if you think of rasterization as having an outer loop where you loop over all the triangles in a scene, and then the hardware can tell you which pixels each triangle touches and color them in, then ray tracing has an outer loop that loops over all the pixels on the screen, and then the hardware figures out which triangle it touches, and then you color it in. But that doesn't really answer the question, or it's the wrong question. What we want to know is, why should we care about ray tracing? What can it do to make my game better? And the simple answer to that is it can make really nice pictures. We can go from something like this to something like this.
Yeah, that's like what
and I'm going to use this image a lot later on because I like it. And without ray tracing, this kind of image would be tricky to produce, or without offline baking, really. You have things like a nice, subtle, soft shadow behind this pillar. And the shadow's not cast from any direct light source, it's cast from these openings here, which are just letting in some daylight, and there's another one that's hidden behind the column. And also you get things like the ceiling here by the entrance is brighter just naturally. We can have things like coloured shadows by tracing through semi-transparent materials and keeping track of the transmission colour. And we can have reflections that can reflect things that are not on the screen. Now, a reasonable chunk of this talk will be about global illumination, and specifically per pixel global illumination. So first I want to talk a little bit about ambient occlusion and how it differs from global illumination. And a lot of you probably have a pretty good idea about what ambient occlusion is. It's the thing that makes corners and crevices dark. But what is it really? Ambient occlusion asks the question, how much can a point see the ambient light, or how much ambient light can get to a point? But it has nothing to say about what the ambient light is, where it's coming from. The simplest form of AO will use the sky as ambient light. So AO's question is, how much can a point see the sky? How is the sky visible? But games which are inside buildings or in rooms, the sky is no good. So they will use light probes maybe to encode what the ambient light is. But whatever the source of the ambient light is, ambient occlusion is used to attenuate it when it estimates that some of the ambient light is blocked. Now, global illumination, on the other hand, is concerned with what is the light that is falling onto a point. What are the local lighting conditions? In Minecraft, we try to get close to per pixel global illumination using ray tracing, in much the same way that most ambient occlusion techniques are done per pixel. And this actually makes the whole thing quite simple. By having per pixel GI, we don't need ambient occlusion. It's already doing that job and more. It solves the problem directly, and it can produce some nice results. So this picture nicely demonstrates some of this. It's a cave with a hole in the roof. There's, the only light sources here are the sky and the sun. So you've got this patch of ground here. This is directly lit by the sun, so it's nice and bright. There's this patch on the floor. Maybe it's not directly lit by the sun, but it can see the sky through the hole, so it's getting direct lighting from the sky, if you like. And then areas here, this bit can't see the hole in the roof at all, so it can't see the sky or the sunlight, so it's shadowed. But what's going on up here? On the ceiling, this part of the ceiling also can't see the hole in the roof, so it can't see the sky or the sun, but it's still lit. And it's lit from the bounced light from this area on the ground. If you were to put yourself up there, you would see this has been quite a bright patch. So there's light coming from there, and that's illuminating the ceiling. We actually have enough detail that you can see some shadows from this bright area here. And here's another example where you can see light bouncing. You can also see the opposite of ambient occlusion as well. This area here, or this area here, the corners aren't darker, they're brighter, because the light is bouncing very close. So let's backtrack a little bit and go back to basics. What does ray tracing hardware through an API like DXR give us? Well, it just tells you what array has hit, what triangle, what object. It doesn't tell you what color it is. But for most of this talk, I'm going to assume the existence of some magic code that lets us ask what the incoming radiance is from any point in any direction. Or if I put myself in a particular position in the world and look in a particular direction, what color do I see? Now remember that ray tracing hardware just tells us what surface the ray has hit. And our magic code then will figure out all the lighting for that point, shade the surface and calculate what the radiance is coming back along the ray that we're asking for. Now of course, if this actually existed, we could just use this for all our primary camera rays, ask it what the color is coming along each camera ray, and that's our image, finished. So just go with me on this. This is cheating, but I promise I will circle back at the end and we'll explain what we actually do. Oops. So let's start simple. We'll do the ray tracing equivalent of deferred shading. So we start with a G buffer. And you could use rasterization to write the G buffer. In Minecraft we use ray tracing, but it doesn't matter. And then we're going to use ray tracing to shade each of the pixels in the G buffer. We can do this by shooting a lot of rays from the surface of each pixel in the G buffer in random directions using the hemisphere described by the surface normal. Now remember, we're cheating so that each ray we shoot, it can tell us what the color is coming from that direction, what the light is. Each ray is one sample of incoming light. And for each ray, we're just going to do very simple Lambert diffuse shading, just plain n.l. And in this case, L, the light direction, is the direction of the ray that we're sampling, because we are literally sampling the light from that direction. And then we just average the results for lots of rays, and you have the results for the pixel. Repeat for all the pixels, and you have an image. So how many random rays does it take to make a nice image? We'll keep things simple. We'll just do simple Lambertian n.l lighting for each sample, and we'll see what we get. So here's a reference image of what we're trying to achieve. And this is what it would look like, excuse me, if we had a lot of samples. Shoot a lot of rays for each pixel. Now just to be clear, this is pure Lambert shading, just diffuse only. So this is with a single ray per pixel, and we wouldn't really expect this to look very good, and it doesn't. It's very noisy, as you might expect, because each pixel is sampling light from a different random direction to its neighbours. There's 2 rays, 4 rays, 8, 16. Now at 16 rays per pixel, we can kind of see what the image would look like if we squint a little bit, but it's still very noisy. 32, 64, 128, 256, and I'm going to stop there, because here we are at now more than 500 million rays for a single 1080p image, and it's still not very good. It's still noisy here and on the floor. So the problem is we need a lot of rays to make a good image, far too many to be practical. So how do we do better? So first I'm going to introduce a concept called importance sampling. Now, importance sampling is quite a simple idea, but it can get complicated quickly. To start with, we're just going to shoot rays completely randomly. Now if you're going to shoot random rays, it's important to make sure that they are uniformly random. It's easy to come up with a function that generates a random point on a hemisphere that you can then use as a direction. But you have to be very careful to make sure that it really is uniform. So here's a function that does generate a uniform distribution. And that uniform distribution looks like this. It looks uniform. So with importance sampling, the idea is that instead of shooting rays, excuse me, instead of shooting rays in completely random directions, you can do better if you can shoot more rays in directions that are more useful, fewer rays in directions that are less useful. But that on its own isn't enough. You have to balance the books. If you don't balance the books, then you will have biased results, and that means incorrect lighting. And to balance the books, you have to be able to calculate an appropriate weight for each ray, so that the directions that are less likely have larger weights to compensate. And I will try and illustrate this with a completely contrived example. So here's a hemisphere with a uniform random distribution of directions. Now let's imagine that, for whatever reason, we want to shoot twice as many rays to the left than the right, because we know there are more useful things in that direction. We can easily do that by making some simple changes to the 2D random numbers before converting to a hemisphere coordinate like this. So don't worry too much about this code. All it's doing is it's taking the middle third range of numbers, so from 0.33 to 0.67, and it's stretching that out to occupy at half, so 0.25 to 0.75, and then squishing in the outer thirds. And the result is this. So now this is biased. Light from the left will have twice as much influence as light from the right, because there are twice as many samples there. So we need to balance the books, and we can do this by adjusting the weights so that samples to the right have twice the weight as samples on the left. And we can show this on the picture by adjusting the area of the blobs. But we need to be very careful that the average weight is still 1, and here this isn't the case. If we have 3 samples, 1 in each third, then you can see that the average weight is actually 4/3, because we've got weights of 1, 1 and 2. So that means to correctly normalize, to correctly rebalance this, we need to multiply all the weights by 3/4, like this. Now it's balanced again. So that's a completely valid but completely useless example of importance sampling. So how about a less contrived example, something a little bit more useful? Now probably the simplest form of importance sampling that's actually useful is called cosine weighted sampling. And this uses the fact that rays at shallow angles to a surface are less important because of the cosine rule, n.l. Cosine weighted sampling bunches the samples more towards the surface normal. So there are fewer samples taken at grazing angles and more samples taken at angles that are more important. But it also calculates an appropriate weight for the samples so that the result remains unbiased, like this. So an interesting side effect of this is the weight that it calculates is proportional to 1/n.l. So as an extra benefit, you can cancel out the n.l from the lighting calculation. So what does this do to our image? Well, it makes it better. It reduces the noise. So this is the 16 sample per pixel image. You can see with the uniform random distribution, we have a lot more noise in this area than we do with the cosine weighted distribution. But it's not fixed it. It's not perfect. It's better for the same number of rays. So what we'd really like to do is be able to do something that gets us down to 1 sample per pixel. And we're not there yet. Now, importance sampling gets really useful and really complicated when you start looking at specular distributions. Now, these are more complicated because there are more parameters. A cosine weighted distribution is fixed, but specular distributions change with things like the view direction and surface roughness. In Minecraft, we use a distribution called VNDF, which works remarkably well and is way better than doing random sampling. So continuing with this problem of how to get good images with a small number of samples leads to my next topic. So denoising is an umbrella term for a family of techniques that really make ray tracing, real-time ray tracing possible. As the name suggests, denoising techniques try to take a noisy signal and make it not noisy, all while maintaining as much detail as possible. Denoising is grounded in a couple of reasonably obvious principles. The pixels that are close to one another often have very similar lighting environments. Often, not always. And the surfaces represented by pixels in the world often have similar lighting environments between frames. So denoising tries to share lighting samples between pixels and between frames where appropriate. And this can effectively increase the number of samples, the number of lighting samples available for a pixel by a lot. But choosing what we're going to denoise is very important. Now you might think that we could just denoise the final image, but that would actually be extremely challenging. If we're going to denoise the final image, then to avoid just having a blurred mess, the denoiser would have to skip pixels that have a different surface color. So it would have to be able to look at pixels next to each other and say, okay, well, this is different, so I can't share the sample. And that would severely restrict how many samples pixels can share, because the colors are changing all the time on a surface. So what if we denoise the incoming irradiance instead? We take the surface color out of the equation. So this signal is a lot smoother now because we don't need to worry about all the detail in the surface color. So you can see that there are a lot more opportunities for denoising, blurring, lots of large flat surfaces. Like you can imagine blurring across all of this area here, and that would work well. But we still have surface normals in normal maps, and these present a discontinuity for the denoiser. So we have a choice again of either blurring across them, in which case we will just lose all of the detail in the normal maps, or we make the denoiser kernel stop when it sees a normal discontinuity, a change in normal. But if we do that, we'll have fewer samples again that the denoiser can work with. So we'll have a noisier image. So again, we're left with this choice. If we stick with this thing that we're going to denoise, we have a choice between blurring normal maps or more noise. So in Minecraft, we use a simple form of spherical harmonics to store the irradiance for the diffuse lighting.
Graphics cards from AMD/console.
Doing this allows us to sample the incoming lights using the geometry normal instead of the surface normal.
The only thing we've seen so far is the demo back during March.
Recover an estimate of irradiance around the surface normal later on in the final lighting pass.
I mean, obviously you can run Minecraft DXR on PC with an RX 6000 graphics card. The performance is not very good because there's no super resolution right now.
So we have much larger smooth areas that the denoiser can work across.
It'll work.
So now the whole floor here, you can imagine blurring across the whole floor and the whole of this column
AMD for Minecraft
and these
DXR.
columns. Let's do that. In Minecraft, we use a version of a technique called SVGF, which stands for Spatiotemporal Variance Guided Filtering for the diffuse denoising. And the special source in this technique is the variance guided bit. SVGF is a big blur, but it's a blur that is geometry aware, so it won't blur across geometric boundaries. And this aspect of the algorithm has been heavily customized for Minecraft, because in Minecraft all the geometry is made up of planar surfaces. So the logic to determine if pixels are part of the same surface can be simplified. Now the image here is what we get when we apply the SVGF blur kernel to our diffuse spherical harmonics, but without using the variance guiding. If we convert this back to a diffuse irradiance color, then it's easier to visualize. Now the problem here is that the blur has eaten away a ton of detail in the shadow, resulting in some really nasty Peter Panning for this column. The column looks like it's floating. But SVGF uses the statistical variance of the luminance to guide the blur kernel weights. So it blurs more when it can and less when there is more detail going on. And the results are amazing. So now the Peter Panning has almost entirely gone. And I think this is remarkable. I think this is amazing to think that you can get a result like this from one sample per pixel. So again, there will be some links at the end to read more about SVGF. This is just a high-level overview. So now all we need to do is bring all the elements together to produce a final image. So now we can use the surface normals again and ask the spherical harmonics what the irradiance is in the direction of the surface normals. Then we can bring in the diffuse color to apply the Lambertian diffuse. So that's our final diffuse denoised image. And then we bring in everything else that we haven't talked about yet, like the specular pass. I promised that I would justify my use of blatant cheating.
Wasn't ray tracing for Minecraft developed by like
what the radiance is from any point?
No, what you're thinking of is that during the March visit,
we need to know
DF and
what
Austin
array
Evans
in
were
that
told
direction
that
hits.
And
then we need to know all about the
Minecraft DXR port, like
so
tech demo port to the Series X, was done by one person over a month.
So how do we know what the lighting is at this new point? Well, we can
Minecraft DXR as a whole was
and now we're back to where we started.
Collaboration between Mojang and NVIDIA with multiple people. But the Xbox tech demo port was one person.
Offline path tracing solves this recursive problem by doing just that. It shoots rays recursively. And it keeps going until a fixed recursion depth is reached, or the ray hits a purely emissive surface, a light source. It's extremely effective, but also extremely expensive. But we can get quite good results by cheating. In Minecraft, we use irradiance caches to move those additional bouncers into a background process that bounces rays over time. We actually store outgoing irradiance in geometry data per face, and we update it over time by continually shooting rays in the background to refine the estimate and keep up with any lighting changes like the movement of the sun. And it looks crude, but it's used when we're sampling random diffuse rays, and even then this version of the cache is only used for rays that hit quite far away. For closer rays, we have a more detailed cache. Here we cache incoming irradiance per vertex and use that along with the diffuse albedo and any self-emissive properties to get a more accurate estimate. But the point of these caches is that they are extremely cheap to look up, and they give us a good estimate when we want to ask what is the radiance from this point and in this direction. So that's the cheating that we do.
Right. The radiance caching is why you kind of see this fade-in effect.
There's one more topic that I want to introduce, and that's the problem with small, bright things.
Kirby just answered. I watched the whole thing.
Just to be clear, when I'm talking about small things, I'm talking about small things in the angular sense. So this cow is small, this cow is far away, but both cows subtend the same angle from the viewer. Random sampling for diffuse irradiance can become problematic when you have small bright things in the scene. The low chance of rays hitting these things, coupled with the high brightness of them, leads to a problem called fireflies. But we want to have things in Minecraft that happen to be small and bright, like torches. So what can we do? We would like lots and lots of small torches, all able to cast shadows. We know random sampling doesn't cut it because they're too small, because of fireflies. What we need is something like importance sampling, but for explicit light sources. Something that can guide the rays towards important lights and calculate appropriate weights. So let's think about this for a second. The starting point is to say that let's just sample from every light for every pixel, and this will give us the right answer. But I hope you can see that it's not very practical if you've got more than a few lights. What we'd like from a practical standpoint is to only sample or shoot a ray to a single light for each pixel. Can we do that? If we just choose one light at random, we're choosing one light from n lights, the total number of lights in our scene. So the balancing weight here is n. And for a small number of lights, with a good denoiser, this can work well. But can we do better? The difficulty comes from figuring out what constitutes an important light. Important lights for one pixel aren't necessarily important for another. How do you figure that out? How do you figure that out without iterating over all of the lights for every pixel just to figure out which ones are the important ones? The technique that we use in Minecraft is effective for maybe a few hundred lights. Each pixel we choose a completely random subset of lights. We choose 8. And then from that subset we calculate an importance for each one using something like the apparent brightness of the light at the point that we're sampling. And then we pick one of those 8 at random, but a weighted random selection using a table of their cumulative importance values. So the chance of a light in the subset being selected is that light's importance divided by the total importance of all 8 lights. Now, direct sampling is a very active area of research right now, and things are moving very rapidly. So I highly recommend watching Chris Wyman's talk on RTX DI for the current state of the art in sampling from millions of lights. Real-time ray tracing adds many possibilities to what we can do for visuals in games.
Again, having someone who understands
in this talk, I've barely scratched the surface on a few topics, but there are lots and lots of topics, even just for Minecraft, that I haven't even touched on.
The panel wants
and hopefully this has piqued some interest. Maybe you can think about how you can start to add ray tracing to your game. Thank you for watching.
That's simple. Right, end of the session. Hold on, I gotta close this and that and that, and now let's go full screen. All right, I'll hit up the other low. Okay, yeah. Right now I actually have to go do something right away. I know I said I would try to answer people's questions, but I just something has come up. It's not like I'm fine. It's just like I got to go do something right now. So just want to say thanks for showing up on my stream and for all the people who talked, asked questions. And hopefully I can do something similar in the future.